Since the dawn of human consciousness, we have gazed at the stars and wondered, where did all of this come from? Did the universe emerge from absolute nothingness, or has something always existed? This question represents perhaps the most profound mystery we can contemplate, the ultimate origin of everything, including space, time, matter, energy, and even the laws of physics themselves. The concept is so vast that it stretches the limits of human comprehension, yet we continue to pursue it with a passion that spans civilizations and millennia. From ancient campfires to modern observatories, humans have crafted stories and theories about cosmic beginnings, each generation building upon and sometimes revolutionizing the ideas of those who came before. This persistent quest speaks to something fundamental in our nature, a deep-seated need to understand our place in the cosmos and how the stage upon which our lives unfold came to be. Throughout history, civilizations have offered their own answers to this ultimate question, creating rich tapestries of myth, philosophy, and early science to explain what cannot be directly observed. Ancient Egyptians envisioned the universe emerging from a boundless primordial ocean called Nun, from which the creator deity Atum arose to establish order. In Babylonian cosmology, the universe began with the gods of freshwater and saltwater, Apsu and Tiamat, whose divine union initiated creation. Hindu traditions speak of endless cycles of creation and destruction, with universes emerging from and returning to Brahman in an eternal dance of existence and non-existence. The ancient Chinese concept of Wuji described a primordial state of limitless potential from which the duality of yin and yang emerged, setting the cosmic cycle in motion. These narratives weren't merely primitive attempts at explanation, they were sophisticated frameworks that integrated observations of natural phenomena with deeper reflections on existence itself. Eastern philosophical traditions often approached the question of origins with concepts that still challenge our thinking today. In Buddhist cosmology, the universe has neither beginning nor end, but exists in an infinite cycle of expansion and contraction, a view that bears striking parallels to some modern theories. The ancient Indian philosophical text, Nasadiya Sukta, from the Rig Veda, poses questions about existence before creation that would not seem out of place in contemporary cosmological debates. Then even nothingness was not, nor existence. There was no air then, nor the heavens beyond it. Taoist philosophy emphasized the emergence of complexity from simplicity, with the Tao Te Ching declaring, "The Tao gave birth to one gave birth to two gave birth to three gave birth to all the myriad things." These Eastern approaches often embrace paradox and cyclicity, concepts that Western thought has sometimes struggled to incorporate, but which resonate with certain aspects of modern cosmological theories. Western religious traditions, particularly those stemming from Abrahamic roots, typically proposed a moment of divine creation, ex nihilo, from nothing. The book of Genesis begins with the famous declaration, "In the beginning, God created the heavens and the earth," establishing a linear timeline with a definite starting point. This conception of a universe with a specific moment of creation has profoundly influenced Western thought, science, and culture for millennia. Islamic scholars like Al-Ghazali and Jewish philosophers like Maimonides elaborated on creation theology, wrestling with questions of divine action and temporal beginnings that would later influence Christian theological developments through figures like Thomas Aquinas. The concept of creation from nothing represents one of the most influential ideas in human history, shaping not just religious thought, but providing a conceptual framework that would eventually inform scientific approaches to cosmology. These narratives served not just as origin stories, but as foundational elements of how cultures understood their place in the cosmos, their moral obligations, and the nature of reality itself. Creation myths established cosmic order and human purpose simultaneously, connecting the vast scale of universe formation to the intimate scale of human experience. They provided answers to the existential questions that arise naturally when intelligent beings contemplate their existence. Why is there something rather than nothing? Why these particular structures and patterns rather than others? What is our relationship to the forces that brought everything into being? Even as our scientific understanding has advanced, these questions continue to resonate because they touch on aspects of experience that transcend purely empirical investigation, meaning, purpose, and the limits of explanation itself. Philosophy and science have approached the question of cosmic origins from different angles, sometimes complementing and sometimes challenging each other. Ancient Greek philosophers made some of the first systematic attempts to understand the universe through reason rather than myth. Parmenides argued that nothingness cannot exist, a concept that resonates with certain interpretations of quantum physics today. Heraclitus emphasized constant change and becoming, while Democritus proposed that indivisible atoms moving through empty space could explain all phenomena. Aristotle, whose views dominated Western thought for nearly 2 millennia, argued for an eternal, uncreated universe, rejecting the possibility of absolute nothingness. His conception of an unmoved mover represented an early attempt to resolve the logical problems of ultimate causation without requiring a beginning of time, a philosophical challenge that remains unresolved. Medieval philosophers across Islamic, Jewish, and Christian traditions grappled with reconciling revealed religion with Greek philosophical inheritance, particularly Aristotle's eternal universe. Thinkers like Al-Kindi, Saadia Gaon, and Thomas Aquinas developed sophisticated arguments about causation, necessity, and contingency to demonstrate the logical requirement for a first cause or necessary being. The famous Kalam cosmological argument, developed by Islamic scholars and later adopted by Christian philosophy, contends that whatever begins to exist must have a cause. The universe began to exist. Therefore, the universe has a cause. These arguments attempted to establish not just religious truth, but logical necessity for a creator, engaging with profound metaphysical questions about why anything exists at all, and whether an infinite regress of causes is possible. As the scientific revolution unfolded in Europe, a more empirical approach to cosmology began to emerge. Copernicus, Galileo, and Newton developed mathematical models and observational methods that transformed our understanding of the universe. Yet even Newton, whose laws of motion and gravitation unified terrestrial and celestial physics, believed in divine creation and saw his work as revealing God's mathematical design. For scientists of this era, explaining the mechanics of the universe did not eliminate the need for an ultimate explanation of its existence. The question remained, even if we understand how the universe works, why does it exist at all? Science could describe, with increasing precision, the patterns and relationships within the cosmos, but the fundamental mystery of being persisted alongside increasingly sophisticated natural explanations. The philosophical landscape shifted dramatically with Immanuel Kant, who argued that questions about ultimate beginnings may be fundamentally unanswerable because they transcend possible human experience. In his Critique of Pure Reason, Kant demonstrated that when human reason attempts to extend beyond experience to grasp the absolute beginning or infinite extent of the cosmos, it becomes entangled in contradictions. His concept of antinomies, equally plausible but contradictory arguments about whether the universe has a beginning, suggested that such questions might be beyond the reach of human knowledge. This Kantian perspective continues to influence philosophical approaches to cosmology, reminding us that our cognitive architecture itself may limit our ability to comprehend absolute origins. We may be like fish, trying to understand the concept of dryness, structurally incapable of directly experiencing what we seek to understand. Science, with its empirical methods, seeks observable evidence and testable theories rather than pure reasoning or revelation. The scientific approach to cosmological origins gathered momentum in the early 20th century with Einstein's theory of general relativity, which provided a mathematical framework for understanding the universe as a dynamic, evolving system rather than a static background. When Alexander Friedmann and Georges Lemaitre independently derived solutions to Einstein's equations suggesting an expanding universe, the foundation was laid for what would become the Big Bang theory. Importantly, This theory emerged not from philosophical speculation, but from mathematical analysis, and was subsequently supported by Edwin Hubble's observations of receding galaxies. For the first time, science offered a data-driven narrative of cosmic beginnings based on backward extrapolation from observed expansion. Yet both philosophy and science face the same fundamental limitation. How can human minds, evolved on a tiny planet to solve practical problems of survival, ever truly comprehend the origin of everything? Our brains develop to track social relationships, find food, avoid predators, and navigate landscapes, not to grasp quantum fluctuations or 11-dimensional superstrings. Our intuitions about cause and effect, about something coming from nothing, about time and infinity, were shaped by experiences within middle-world scales of size and energy. When we attempt to understand reality at the Planck scale, or across billions of light-years, we push our cognitive capabilities beyond their evolved parameters. This isn't merely a technical challenge, but potentially a fundamental constraint on human understanding. Our languages, too, may impose limitations on our ability to conceptualize cosmic origins. When we ask, what came before the beginning, or what caused the first cause, we employ syntactic structures that presuppose time and causality, the very concepts that may break down at the threshold of existence. Even our most basic philosophical questions about nothing, why is there something rather than nothing, may contain hidden assumptions that presuppose frameworks of logic and possibility that themselves require explanation. The challenge extends beyond our biological limitations to include cultural, linguistic, and conceptual constraints that shape how we frame the question of beginnings. We may be asking questions that are structurally flawed, using frameworks inadequate to the task at hand. Perhaps we can never know, with absolute certainty, how everything began. Our instruments can only peer so far back in time. Our mathematics can only model so much complexity, and our minds can only grasp so many abstractions. The cosmic microwave background radiation, the oldest light in the universe, provides a window to conditions about 380,000 years after the initial expansion began. But earlier epochs remain hidden behind a wall of opacity. Theoretical physics can model conditions approaching the Planck time, approximately 10 to the negative 43 seconds after the beginning, but cannot yet penetrate to the hypothetical time zero. We face not just technical limitations that might be overcome with better instruments or more advanced mathematics, but potentially fundamental epistemological barriers that no amount of scientific progress can surmount. Yet despite these profound challenges, the question of cosmic origins matters profoundly. It sits at the intersection of our greatest intellectual pursuits and most profound existential concerns. For physics, understanding the initial conditions of the universe represents the ultimate boundary value problem, the starting point from which all natural laws and physical constants must emerge or be explained. If we cannot account for why certain forces have the strengths they do or why certain particles have the masses they possess, our understanding remains fundamentally incomplete. The origin question drives theoretical physics toward ever more comprehensive theories that might unify the fundamental forces and explain the apparent fine-tuning of physical constants that allow for complex structures and, ultimately, life. For cosmology, the question of beginnings frames our understanding of the universe's evolution and ultimate fate. Our models of cosmic evolution, from inflation through nucleosynthesis to structure formation and eventual heat death or big rip, all depend on initial conditions and governing laws that themselves require explanation. Does the arrow of time that we observe, with entropy increasing and complexity emerging then dissolving, extend infinitely backward and forward, or does it have a beginning and end? Does the apparent acceleration of cosmic expansion point toward a universe that will expand forever into cold emptiness? Or might some currently unknown process reverse this trend? These questions about cosmic destiny connect intimately with questions about cosmic origins, forming a complete temporal arc that contextualizes all other scientific inquiries. For philosophy, The origin question challenges our most fundamental concepts: causality, existence, time, necessity, possibility, and the limits of knowledge itself. It forces us to examine whether our intuitive notions of cause and effect apply at the scale of the entire cosmos, whether time itself is fundamental or emergent, whether mathematical structures exist independently of physical reality, and whether explanation can ever be truly complete. The question of why there is something rather than nothing has been called the ultimate why question, because it seems to demand a different kind of answer than other scientific or philosophical questions, one that would somehow stand outside the framework of contingent existence and provide a necessary foundation for everything else. And for many individuals, regardless of their scientific or philosophical sophistication, the question connects to deeply personal concerns about meaning and purpose. If the universe emerged randomly from quantum fluctuations, does that make human existence merely accidental? If cosmic beginnings required precise fine-tuning of physical constants, does that suggest purpose or design? If multiple universes exist with different physical laws, does that diminish the significance of our particular cosmic home? These questions about meaning do not follow logically from scientific findings, but they arise naturally when humans contemplate their place in the cosmic story. The origin question thus bridges the objective pursuits of science with the subjective quest for meaning that characterizes human consciousness. What we do know with reasonable confidence is that our observable universe has been expanding for approximately 13.8 billion years, with all matter and energy originating from an incredibly hot, dense state. This model, commonly called the Big Bang Theory, represents one of the greatest achievements of modern science, a comprehensive framework supported by multiple independent lines of evidence that explains the observed features of our cosmos. It does not claim to describe the absolute beginning or explain why there is a universe at all, but it provides a rigorously tested account of cosmic evolution from a small fraction of a second after whatever initiated the process of expansion. The theory's predictive power and explanatory scope make it the foundation of modern cosmology, even as researchers continue to refine and extend it. The empirical support for the Big Bang Theory comes from several directions, creating a robust web of evidence. First, and perhaps most famously, we observe that galaxies are moving away from each other in a pattern consistent with expansion from a common origin. Edwin Hubble's discovery in the 1920s that distant galaxies show redshifts proportional to their distance suggested that space itself is stretching, carrying galaxies along like raisins in an expanding loaf of bread. This observation alone doesn't prove a singular beginning, but it does establish that the universe has a dynamic history rather than being static and eternal in its current form. When we mathematically reverse this expansion, we find that all matter and energy would have been compressed into an extremely hot, dense state about 13.8 billion years ago, the starting point for the Big Bang model. Perhaps the most compelling evidence for the Big Bang comes from the cosmic microwave background radiation, the afterglow of the early universe discovered accidentally by Arno Penzias and Robert Wilson in 1964. This faint microwave signal, coming uniformly from all directions in space, represents light released when the universe cooled enough for electrons and protons to form neutral hydrogen atoms, allowing photons to travel freely for the first time. The properties of this radiation, its temperature, spectrum, and subtle variations, match predictions made by the Big Bang Theory with extraordinary precision. Space telescopes like Kuiper, WMAP, and Planck have mapped minute temperature fluctuations in this background radiation, revealing the seeds of cosmic structure that would eventually grow into galaxies and galaxy clusters through gravitational attraction. The patterns in these fluctuations provide a kind of cosmic fingerprint that strongly supports not just the Big Bang model, but specific details about the composition and dynamics of the early universe. Another powerful line of evidence comes from the abundance of light elements in the cosmos. The Big Bang Theory predicts that during the first few minutes of expansion, conditions would have been perfect for nuclear fusion to create significant amounts of deuterium, helium, and lithium, but not heavier elements, which would form later in stars. The observed cosmic abundances of these elements, roughly 75% hydrogen, 24% helium, and tiny traces of other light elements, matched the predictions of Big Bang nucleosynthesis models with remarkable accuracy. This agreement between theoretical calculations and astronomical observations across billions of light years provides strong support for the hot, dense early state described by the Big Bang theory. The precise ratio of hydrogen to helium serves as a kind of chemical fossil record of conditions in the very early universe, allowing us to test our models against reality. The large-scale structure of the cosmos, the distribution of galaxies, galaxy clusters, and cosmic voids across space provides yet another confirmation of the Big Bang model. Detailed sky surveys have mapped hundreds of thousands of galaxies, revealing a cosmic web of filaments and clusters with voids between them. Computer simulations based on Big Bang conditions and the physics of gravity reliably reproduce these observed structures, demonstrating that our understanding of cosmic evolution is fundamentally sound. The size and distribution of these structures match what we would expect if small density fluctuations in the early universe, visible as temperature variations in the cosmic microwave background, gradually grew through gravitational attraction over billions of years. This consistency between early conditions and current structure strongly supports the Big Bang narrative of cosmic development. But the Big Bang theory isn't a complete explanation of origins, and this is a crucial point that is often misunderstood in popular discussions. It doesn't tell us what caused the initial expansion, what, if anything, existed before it, or why the universe has the particular properties it does. The mathematics of general relativity, our best theory of gravity, breaks down when we try to model the very first fraction of a second, leading to singularities where physical quantities become infinite and the equations lose their predictive power. At extremely small scales and high energies, we need a theory of quantum gravity that we don't yet fully possess, despite promising approaches from string theory, loop quantum gravity, and other frameworks. The Big Bang represents the limit of our current understanding, rather than a complete account of absolute beginnings. The standard Big Bang model begins at an incredibly small fraction of a second after whatever initiated the expansion, typically around 10 to the negative 36 seconds in models that include cosmic inflation. Before that lies a theoretical region physicists call the Planck epoch, a period so early and extreme that our current understanding of physics cannot reliably describe it. During this epoch, all four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, may have been unified into a single superforce, and the very concepts of space and time, as we understand them, may not have been meaningful. This is the frontier where our knowledge meets its limits, where speculation begins to replace certainty, and where the most profound questions about origins remain unanswered. To understand the origins of everything, we must first understand what the Big Bang really means and what it doesn't mean. Popular descriptions often characterize it as an explosion, but this is misleading. The Big Bang wasn't an explosion in pre-existing space, but rather the rapid expansion of space itself. It doesn't necessarily imply an absolute beginning from nothing, but rather a boundary to our current knowledge. All matter, energy, space, and time as we experience them may have emerged from this expansion, but this doesn't preclude the possibility of other forms of existence before or outside our observable universe. The Big Bang is less a creation event and more the earliest state of the universe that we can model with confidence using our current theoretical frameworks. As we peer deeper into this mystery, we must confront profound questions that challenge not just our scientific knowledge, but our conceptual frameworks. Is absolute nothingness, the complete absence of space, time, matter, energy, laws, or potential, even physically possible or logically coherent? Could the universe be self-causing or eternal in some way that transcends our linear notion of time? Are our concepts of time and causality merely human constructs that break down at the cosmic scale? requiring entirely new modes of understanding. Is our universe unique, or is it one bubble in a vast multiverse of different realities, with different properties and histories? These questions lie at the frontier of human thought, where science, philosophy, mathematics, and even theology offer complementary perspectives. Some cosmologists suggest the universe may have emerged from quantum fluctuations in a pre-existing state, perhaps a quantum vacuum with different properties than our current vacuum. Others propose cyclical models where big bangs and big crunches alternate eternally, or where brains, membrane-like structures in higher dimensions, periodically collide to create new cosmic expansions. String theorists explore whether higher dimensions or parallel universes might provide a larger context for our cosmos, potentially explaining why our universe has the specific physical constants that allow for complexity and life. Philosophers continue to debate whether the universe requires an external cause or could be self-explanatory, whether time has an absolute beginning or extends infinitely, and whether the question, why is there something rather than nothing, can ever receive a satisfying answer. Each approach brings new insights, but also new questions. A quantum origin still requires us to explain the existence and properties of quantum fields. Multiverse theories push the question of origins to a higher level without necessarily resolving it. Cyclical models face entropy challenges and questions about information transfer between cycles. Mathematical universe hypotheses must account for why certain mathematical structures are physically realized while others are not. The quest for ultimate origins seems to generate an infinite regress of explanations, with each answer raising new questions about its own foundations. Perhaps this pattern itself tells us something important about the nature of explanation and the limits of human understanding. The quest to understand our ultimate origins stretches the limits of science, philosophy, and human comprehension. It requires humility about what we know, curiosity about what we don't, and openness to ideas that may seem counterintuitive or strange. It demands mathematical precision alongside conceptual flexibility, empirical rigor alongside metaphysical insight. Most of all, it requires intellectual honesty about the boundary between established knowledge and reasonable speculation, between what we can conclude with confidence and what remains mysterious. As we continue our journey through the cosmos and through the landscape of human knowledge, we carry this fundamental question with us, perhaps never to be fully answered, but always to be explored more deeply. Was there ever truly nothing? To begin answering this question, or at least to approach it with greater clarity, we must first examine in detail what we know about the early universe and what the Big Bang theory actually tells us about our cosmic origins. The evidence is compelling, the scientific consensus strong, but the story it tells is still incomplete, particularly at the earliest moments and largest scales. By understanding the strengths and limitations of our current best theory, we can better appreciate where the true mysteries lie and how future discoveries might illuminate them. The next chapter of our exploration takes us deep into the physics of the Big Bang, the evidence supporting it, and the crucial questions it leaves unanswered about the ultimate beginning. The Big Bang theory stands as one of humanity's greatest intellectual achievements, a comprehensive framework that explains the evolution of our universe from a hot, dense state to the vast cosmic web we observe today. First proposed in its earliest form by Belgian priest and physicist Georges Lemaitre in 1927, the theory has withstood nearly a century of rigorous testing and refinement. Yet despite its name, the Big Bang was neither big in the conventional sense. The initial expansion occurred at all points in space simultaneously, nor a bang, which would imply an explosion into pre-existing space. Rather, it represents the rapid expansion of space-time itself, carrying energy and the potential for all future matter with it. When cosmologists speak of the Big Bang, they're referring to a process rather than a single event, the ongoing expansion of the universe from an extremely hot, dense initial state. This expansion isn't like an explosion from a central point, but rather the stretching of space itself, with every region moving away from every other region, like dots on an inflating balloon. The theory doesn't actually describe the hypothetical time zero or singularity, but rather the evolution of the universe from a small fraction of a second afterward, when temperatures and densities were extreme but finite. The mathematical foundation for the Big Bang theory came from Albert Einstein's general theory of relativity, published in 1915, which described gravity not as a force, but as the curvature of space-time caused by matter and energy. When Einstein applied his equations to the universe as a whole, he found that they predicted either an expanding or contracting cosmos, a result so at odds with the prevailing view of a static, eternal universe that he added a cosmological constant to maintain cosmic stability. This mathematical adjustment was, by Einstein's own later admission, his greatest blunder, as it prevented him from predicting the expanding universe that would soon be observed. The theoretical possibility of an expanding universe became observational reality through the work of Edwin Hubble, who in 1929 demonstrated that distant galaxies are moving away from the Milky Way at speeds proportional to their distance, a relationship now known as Hubble's law. Using the 100-inch telescope at Mount Wilson Observatory, Hubble measured the redshifts of galaxies and found that more distant galaxies showed greater redshifts, indicating faster recession velocities. This discovery provided the first empirical evidence for cosmic expansion and, by extension, support for what would later be called the Big Bang theory. The Big Bang theory gained decisive support in 1965 with the discovery of the cosmic microwave background radiation, CMB, by Arno Penzias and Robert Wilson at Bell Laboratories. Working with a sensitive radio antenna, they detected a persistent microwave signal coming uniformly from all directions in the sky. This omnidirectional radiation had precisely the characteristics predicted as a testable consequence of the Big Bang model. A thermal spectrum corresponding to a temperature of about 3 degrees Kelvin, representing the greatly redshifted afterglow of the early hot universe. The CMB observation provided powerful evidence for a hot, dense, early state, and effectively ended serious scientific consideration of competing steady-state theories. What makes the cosmic microwave background such compelling evidence for the Big Bang is not just its existence, but its detailed properties. The radiation exhibits an almost perfect blackbody spectrum, exactly what would be expected if it originated from matter and radiation in thermal equilibrium during the early universe. The uniformity of this radiation in all directions confirms the cosmological principle that underlies the Big Bang theory, the assumption that the universe is, on the largest scales, homogeneous and isotropic. At the same time, the tiny temperature fluctuations in the CMB, mapped with increasing precision by satellites like COBE, WMAP, and Planck, reveal the seeds of cosmic structure, the slight density variations that eventually grew through gravitational attraction into galaxies and galaxy clusters. The cosmic abundances of light elements provide another powerful pillar supporting the Big Bang theory. During the first few minutes after the Big Bang, conditions were perfect for the production of deuterium, heavy hydrogen, helium-3, helium-4, and small amounts of lithium-7. This process, known as Big Bang nucleosynthesis, depended on specific temperature, density, and neutron-to-proton ratio conditions. The theory makes precise predictions about the resulting abundances, roughly 75% hydrogen, 25% helium-4, and trace amounts of the other light elements. Astronomical observations across billions of light-years confirm these predictions with remarkable accuracy, providing strong support for the hot, dense, early universe described by the Big Bang model. To understand what transpired during the universe's earliest moments, cosmologists have constructed a detailed timeline based on known physics. In the first fraction of a second after the hypothetical beginning, from about 10 to the negative 43 seconds, the Planck time, to 10 to the negative 36 seconds, temperatures were so extreme that all four fundamental forces may have been unified into a single superforce. This earliest epoch represents the frontier of theoretical physics, where our current understanding breaks down and where a quantum theory of gravity would be required to describe conditions accurately, from approximately 10 to the negative 36 to 10 to the negative 32 seconds after the beginning. A process called cosmic inflation may have occurred, an exponential expansion of space at speeds far exceeding the current expansion rate. First proposed by physicist Alan Guth in 1980, inflation theory suggests that a tiny region of space expanded by a factor of at least 10 to the 25th in just a fraction of a second. This inflationary period would explain why the universe appears flat and uniform on large scales, while also accounting for the initial density fluctuations seen in the cosmic microwave background. After inflation ended, the enormous energy that drove the exponential expansion was converted into a dense soup of elementary particles and radiation through a process called reheating. From about 10 to the negative 12 seconds, the universe consisted primarily of a quark-gluon plasma, a state of matter so hot and dense that quarks and gluons moved freely rather than being bound into protons and neutrons. As expansion continued and temperatures fell, quarks combined to form hadrons, including protons and neutrons. During this era, matter and antimatter existed in nearly equal amounts, but a slight asymmetry led to the predominance of matter in our universe when most particles and antiparticles later annihilated. From 1 second to about 3 minutes after the Big Bang, nuclear fusion led to the formation of the lightest elements. During this brief window, roughly 25% of all protons and neutrons fused to form helium-4 nuclei, along with small amounts of deuterium, helium-3, and lithium. The heavier elements that make up a substantial portion of Earth and our bodies were not created during this early phase, but would form much later in stars and stellar explosions. A critical transition occurred approximately 380,000 years after the Big Bang, when the temperature dropped to about 3,000 degrees Kelvin. At this point, electrons combined with nuclei to form neutral atoms in a process called recombination. With electrons now bound into atoms, rather than freely roaming, photons could suddenly travel unimpeded through space. This liberation of light created the cosmic microwave background radiation that we observe today, providing a snapshot of conditions when the universe was less than 1% of its current age. From about 400,000 to 100 million years after the Big Bang, gravity gradually amplified tiny density fluctuations in the matter distribution. Eventually, the densest regions collapsed to form the first stars, likely massive, short-lived giants composed only of hydrogen and helium, which ended the cosmic dark ages and began the process of cosmic reionization as their intense radiation stripped electrons from the surrounding neutral hydrogen. Over the subsequent 13 billion years, cosmic evolution has continued through the formation of galaxies, the birth and death of generations of stars, the synthesis of heavier elements, and the eventual emergence of planets, including our Earth. Throughout this extended history, the universe has continued to expand, with galaxies moving increasingly far apart. About 5 billion years ago, this expansion began to accelerate due to the influence of dark energy, a mysterious component making up about 68% of the cosmic energy budget. Limitations of the Big Bang theory highlight important frontiers in cosmological understanding. The theory doesn't explain why the universe began with extremely low entropy, creating the arrow of time we experience. It doesn't account for the initial conditions that led to cosmic inflation, nor fully explain the mechanism that drove inflation. The theory doesn't explain the origin of the matter-antimatter asymmetry that allowed matter to predominate in our universe. It doesn't elucidate the nature of dark matter or dark energy, which together make up 95% of the cosmic energy budget. And it doesn't address the apparent fine-tuning of physical constants that allow for complexity in life. These limitations don't invalidate the Big Bang theory, which remains our best explanation for a vast array of observations, but they do point to areas where deeper theoretical frameworks may be needed. Does the Big Bang theory imply that nothing existed before the initial expansion. Strictly speaking, the standard Big Bang model describes cosmic evolution from a small fraction of a second after whatever initiated the expansion, not from an absolute beginning or from nothing. The theory itself makes no definitive claims about conditions at the hypothetical time zero or before. When cosmologists extrapolate backward using general relativity, they encounter a mathematical singularity where density and temperature become infinite and the equations break down. But this likely indicates the limitations of our current theoretical framework, rather than proving an absolute beginning from nothing. Multiple theoretical approaches suggest possibilities for what might have preceded the Big Bang. Quantum cohomology models propose that the universe tunneled quantum mechanically from a pre-existing state. Bouncing cosmologies suggest our expansion might be one phase in a cyclical pattern, and multiverse theories embed our observable universe within a larger reality. The Big Bang theory itself remains agnostic about these possibilities, focusing instead on the well-evidenced expansion from an early hot dense state, rather than on ultimate origins. As we continue our exploration of cosmic origins, the Big Bang theory provides our most secure footing, a robust, evidence-based account of the universe's evolution from a hot, dense state to its current vast, complex form. The theory's explanatory power, across multiple independent lines of evidence, makes it one of the most successful frameworks in the history of science. Yet the theory also points beyond itself, highlighting questions about initial conditions, quantum gravity, and ultimate origins that it cannot answer alone. While we may never achieve absolute certainty about the ultimate beginning, whether there was ever truly nothing, the Big Bang theory represents humanity's most successful attempt to reconstruct our cosmic history and place ourselves within the grand narrative of an evolving universe. As we approach the frontier of our cosmological understanding, we confront perhaps the most profound question in all of science. What, if anything, existed before the Big Bang? While the standard Big Bang theory provides a robust framework for understanding the universe's evolution from a fraction of a second after its apparent beginning, it falls silent on the question of absolute origins. This silence isn't merely a temporary gap in knowledge awaiting further data, but potentially a fundamental limitation arising from the breakdown of space, time, and causality as we understand them. When we ask what came before the Big Bang, we implicitly assume the existence of time as we experience it, a linear progression of moments flowing from past to future. Yet if time itself emerged with the Big Bang, as some theories suggest, then the concept of before might be as meaningless as asking what lies north of the North Pole. Nevertheless, theoretical physics has developed several compelling frameworks that attempt to extend our understanding beyond the standard Big Bang model, offering glimpses of what might have preceded our observable universe's expansion. Cosmic inflation stands as perhaps the most widely accepted extension to the standard Big Bang model, addressing several problems that the original theory left unresolved. Proposed by physicist Alan Guth in 1980 and further developed by Andre Linde, Paul Steinhardt, and others, inflation posits that the universe underwent a period of exponential expansion in its earliest moments, increasing in size by a factor of at least 10 to the 25th in just a fraction of a second. This rapid expansion would explain why the universe appears remarkably flat and uniform on large scales, the flatness and horizon problems, and would also account for the pattern of tiny temperature fluctuations observed in the cosmic microwave background radiation. While inflation has become a standard component of modern cosmology, supported by precise measurements of the cosmic microwave background, it pushes the question of origins further back, rather than resolving it. What caused inflation to begin? What existed in the pre-inflationary state? And why did inflation eventually end, transitioning to the slower expansion we observe today? These questions lead us deeper into theoretical territory, where several competing models attempt to describe what might have existed before or caused the inflationary phase. The theory of eternal inflation, developed primarily by Andre Linde, Alexander Vilenkin, and others since the 1980s, suggests that inflation never entirely stops. In this scenario, our observable universe represents just one bubble or pocket universe within a vastly larger multiverse that continuously generates new regions of space through ongoing inflation, while most regions eventually stop inflating and develop into universes like our own. The multiverse as a whole continues expanding exponentially, with new bubble universes constantly forming in different locations. This process has no beginning and no end. It is literally eternal, with our Big Bang representing not the beginning of everything, but merely the beginning of our local cosmic region. In this framework, asking what came before inflation becomes meaningless, as inflation itself is the eternal background state from which all pocket universes emerge. The eternal inflation model elegantly avoids the problem of an absolute beginning, but raises new questions about verification, as regions beyond our cosmic horizon remain permanently unobservable, challenging traditional scientific requirements for testability. Quantum fluctuations represent another possible mechanism for the emergence of our universe from a pre-existing state. According to quantum mechanics, even empty space contains energy in the form of quantum fields, and these fields are subject to Heisenberg's uncertainty principle, which allows for temporary fluctuations in energy or the spontaneous appearance and disappearance of virtual particles. Some cosmological models propose that our entire universe might have originated as a large-scale quantum fluctuation in a pre-existing quantum vacuum state. In this scenario, quantum indeterminacy would have allowed a small region of space to tunnel into a rapidly expanding phase, creating the conditions for the Big Bang. Edward Tryon first proposed this concept in 1973, suggesting that our universe might be a vacuum fluctuation on a grand scale. And later, theorists including Alexander Vilenkin and Lawrence Krauss have further developed models showing how quantum tunneling could lead to the creation of space, time, and energy from a quantum vacuum. While these models provide potential mechanisms for a universe to emerge from a pre-existing quantum state, they still require that state itself to exist, merely pushing the question of ultimate origins back a step rather than resolving it completely. Could space and time emerge randomly from more fundamental entities or principles? Various approaches to quantum gravity, efforts to reconcile quantum mechanics with general relativity, suggest that space-time itself might not be fundamental, but rather emerge from deeper physical or mathematical structures. Loop quantum cosmology, a framework derived from loop quantum gravity, proposes that space consists of discrete units at the Planck scale, approximately 10 to the negative 35 meters, and that quantum effects become dominant at this scale, preventing the formation of a true singularity at the Big Bang. Instead, this approach suggests a big bounce, where a previous contracting phase of the universe reached a minimum size before quantum repulsion caused it to rebound into our current expanding phase. Similarly, string theory and its extensions like M-theory suggest that our four-dimensional spacetime emerges from a more fundamental reality of vibrating strings or branes in higher dimensions. These approaches imply that what we perceive as the beginning of space and time might simply be a transition or boundary between different manifestations of a more fundamental reality, one where our conventional notions of before and after might not even apply. The concept of a cyclic or oscillating universe offers another perspective on what might have preceded our Big Bang. In these models, the universe undergoes endless cycles of expansion and contraction, with each Big Bang followed eventually by a big crunch that leads to another Big Bang. Physicist Richard Tolman explored such models in the 1930s, though they fell out of favor when observations suggested the universe would expand forever rather than recollapse. More recently, Paul Steinhardt and Neil Turok developed an updated cyclic model based on string theory, proposing that our universe exists on a brane, a membrane-like structure in higher dimensions, that periodically collides with another brane, with each collision initiating a new cycle of cosmic evolution. An advantage of cyclic models is that they potentially solve the problem of the universe's remarkably low initial entropy. the highly ordered state that allows for the arrow of time we experience. In a cyclic universe, the apparent fine-tuning of initial conditions might result from natural processes occurring during the previous cycle, making our cosmic environment less improbably special than it might otherwise seem. However, cyclic models face the challenge of explaining how information and order can be transferred from one cycle to the next without violating the second law of thermodynamics, which dictates ever-increasing entropy. Was there a pre-Big Bang state with fundamentally different properties than our current universe? Some theoretical approaches suggest the possibility of a phase transition in the early universe, similar to how water can transform from liquid to solid as temperature decreases. In these scenarios, the apparently singular beginning of our universe might represent a change in the state of whatever existed previously, rather than creation from nothing. For instance, in certain string theory scenarios, the pre-Big Bang universe might have existed in a different vacuum state, with different effective physical laws, dimensional structure, or energy distribution. A transition between vacuum states could appear from our perspective as a beginning of space and time. Similarly, some approaches to quantum cosmology suggest that the universe could have tunneled quantum mechanically from a pre-existing metastable state to our current expanding phase. These models imply continuity at a deeper level, even if conventional spacetime appears to have a beginning in our observable universe. They also suggest the tantalizing possibility that the laws of physics themselves might have a history, emerging or changing through cosmic transitions, rather than existing timelessly and universally as often assumed. The question of whether time existed before the universe as we know it touches on some of the deepest mysteries in physics and philosophy. In Einstein's general relativity, time is not absolute, but is interwoven with space in a four-dimensional space-time fabric that can stretch, compress, and curve in response to matter and energy. Near extreme gravitational sources like black holes, time can slow dramatically. And in the hypothetical singularity at the beginning of the Big Bang, the equations of general relativity suggest that time itself might reach a boundary or beginning point. Yet quantum mechanics introduces fundamental uncertainties at extremely small scales, potentially preventing true singularities and suggesting alternative interpretations of apparent time boundaries. Theoretical physicist Julian Barber has proposed that time itself might be an emergent property rather than a fundamental dimension, a measure of changing relationships between configurations of matter rather than a thing in itself. In his view, our perception of flowing time emerges from correlations between memory states and physically ordered configurations, with no fundamental now moving from past to future. Other approaches suggest that time might have flowed in the reverse direction before the Big Bang, or that our familiar linear time might emerge from a more fundamental, timeless quantum state, described by the Wheeler-DeWitt equation in quantum cosmology. Could our universe have emerged from another universe or a larger multiverse structure? Several theoretical frameworks suggest this possibility. Physicist Lee Smolin's cosmic natural selection hypothesis proposes that black holes in our universe might give birth to new universes with slightly different physical constants, leading to a kind of cosmological evolution where universes that produce many black holes have more offspring and become more common in the multiverse ensemble. Mathematician Roger Penrose's conformal cyclic cosmology suggests that the infinitely expanded state of a previous universe, with all matter decayed to radiation, could become mathematically equivalent to the extremely compressed state of the next universe's beginning, creating cycles of universes connected by conformal transformations. The string theory landscape potentially contains an enormous number of possible vacuum states, perhaps 10 to the 500th or more, each representing a different possible universe with different physical constants and laws, suggesting our universe might be one realization in a vast ensemble of possibilities. These frameworks extend the scope of cosmological thinking beyond our observable universe, suggesting that our Big Bang might be just one of countless universal births occurring within a much larger and possibly eternal multiverse structure. The fine-tuning of physical constants presents a puzzle that has implications for theories about what preceded our universe. The fundamental constants of nature, including the strength of gravity, the masses of elementary particles, the strength of the nuclear forces, and the cosmological constant, appear precisely calibrated to allow for complexity and life. Slight changes to these values would result in universes where atoms couldn't form, stars couldn't ignite, chemistry couldn't function, or matter would immediately collapse or rapidly disperse. This apparent fine-tuning has three main interpretations. It might indicate purposeful design by a creator. It might reflect a natural selection mechanism operating at the multiverse level that favors universes capable of producing observers. Or it might result from a multiverse containing universes with all possible parameter values, where we necessarily find ourselves in one compatible with our existence, the anthropic principle. If the multiverse interpretation is correct, fine-tuning would provide indirect evidence for a reality beyond our observable universe, one where different regions manifest different physical laws, with our particular cosmic environment being just one possibility among many. This perspective transforms what appears as an improbable cosmic coincidence into an expected consequence of a diverse multiverse, suggesting our universe emerged from a process that generates tremendous cosmic variety, rather than appearing in isolation. The concept of a universe from nothing has gained attention through the work of theoretical physicists like Alexander Vilenkin, Lawrence Krauss, and others, who argue that quantum mechanics potentially allows for the creation of a universe without requiring any pre-existing material cause. In this view, quantum fluctuations in a zero-energy state could produce a universe where positive energy in the form of matter is exactly balanced by negative gravitational energy, resulting in a total energy of zero, a kind of cosmic free lunch. This approach attempts to answer the ancient philosophical question of why there is something rather than nothing, by suggesting that, in a deep sense, the totality of existence might still sum to nothing when all positive and negative contributions are accounted for. However, critics point out that this concept of nothing still involves quantum fields, physical laws, and possibilities governed by mathematics, a vacuum state that, while empty of particles, isn't truly nothing in the philosophical sense of absolute non-being. The debate highlights the challenge of distinguishing between different concepts of nothingness: the physicist's nothing, a quantum vacuum state with no particles but with physical laws, versus the philosopher's nothing, the absolute absence of anything, including physical laws, potentials, or mathematical structures. This distinction becomes crucial when considering what might have existed before the Big Bang, or how something could emerge from nothing. The transition from the possible pre-Big Bang state to our observable universe raises profound questions about causality itself. In our everyday experience and throughout scientific practice, we assume that events have causes that precede them in time. Yet at the boundary of the Big Bang, this assumption becomes problematic. If time itself began with the Big Bang, then asking for a cause that came before may be conceptually incoherent. Some approaches to quantum cosmology suggest that the universe might be self-contained both spatially and temporally, with no boundary or edge requiring external explanation, analogous to how the surface of a sphere has no boundary or edge despite being finite. Stephen Hawking and James Hartle proposed the no-boundary proposal in the 1980s, suggesting that asking what came before the Big Bang is like asking what is north of the North Pole. The question itself contains a mistaken assumption. In their quantum cosmological model, time emerges as a dimension only after the universe reaches a certain size, with the apparent beginning point being more akin to the tip of a cone, where one dimension smoothly transforms into another, rather than a true temporal boundary requiring a before and after. This approach attempts to preserve causality while eliminating the need for a cause that precedes the universe in time. Theoretical approaches to what preceded the Big Bang must eventually confront experimental reality. Can they be tested? at least in principle. While we cannot directly observe events before the Big Bang, several proposed tests might provide indirect evidence for different pre-Big Bang scenarios. Certain models of cosmic inflation make specific predictions about patterns of polarization in the cosmic microwave background radiation, potentially revealing gravitational waves produced during the inflationary epoch. These predictions differ between models, offering a way to distinguish between various inflationary scenarios and potentially revealing information about pre-inflationary conditions. Cyclic universe models might leave distinctive signatures in the distribution of galaxies or in gravitational wave backgrounds. Black hole physics might provide insights into quantum gravity effects relevant to the early universe, as both involve extreme gravitational conditions where quantum effects become significant. Laboratory tests of quantum gravity theories, though enormously challenging given the energies involved, might eventually provide evidence for frameworks that extend beyond the standard Big Bang model. While direct observation of pre-Big Bang conditions remains impossible with current technology, the history of science suggests that theoretical developments combined with increasingly precise observations can sometimes reveal aspects of reality that initially seem permanently beyond empirical investigation. The quest to understand what came before the Big Bang transcends traditional boundaries between science, philosophy, and even theology, raising questions about the limits of knowledge itself. Can human minds, evolved on a small planet to solve practical problems of survival, ever truly comprehend the absolute origin of everything? Is our conceptual framework, built on notions of space, time, and causality derived from middle-world experience, adequate for understanding conditions where these concepts themselves break down? The renowned physicist Richard Feynman once remarked that anyone who claims to understand quantum mechanics doesn't really understand it, highlighting how counterintuitive nature becomes at fundamental scales. This challenge becomes even more acute when considering the origin of the universe, where quantum effects combine with extreme gravitational conditions. Yet the history of science offers reasons for cautious optimism. Concepts that once seemed beyond human comprehension, the curvature of space-time, quantum entanglement, the evolutionary origin of complex life, have yielded to systematic investigation and mathematical modeling. While we may never achieve absolute certainty about what, if anything, preceded the Big Bang, the theoretical frameworks developed by cosmologists offer increasingly sophisticated approaches to this ultimate question, expanding the boundaries of what we can meaningfully contemplate about the origin of everything we observe. As we continue exploring the mysteries of cosmic origins, the question of what existed before the Big Bang serves as a humbling reminder of how much remains unknown beyond the frontiers of current knowledge. The standard Big Bang theory, for all its empirical success, cannot tell us whether our universe emerged from absolute nothingness, from a quantum vacuum state, from a pre-existing universe in a cyclical pattern, or as one bubble in an eternal inflationary multiverse. Each possibility carries profound implications, not just for cosmology, but for our understanding of existence itself. Does reality have an absolute beginning, or is it eternal in some form? Is our observable universe unique, or one among countless others? Are the laws of physics themselves contingent, potentially different in other cosmic regions? Or are they necessary, mathematically determined features of any possible reality? As theoretical physics advances and observational techniques become more sophisticated, we may gain new insights into these profound questions. But we should also recognize that some aspects of ultimate origins might lie beyond the reach of empirical science, inhabiting the borderlands where physics meets philosophy and where mathematical models of what might have existed before the Big Bang represent our best approximations of a reality that may exceed our full comprehension. The concept of nothing seems deceptively simple at first glance, the absence of everything, a void without properties or content. This intuitive understanding has shaped philosophical and theological discussions about creation for millennia, from the ancient Greek concept of ex nihilo nihil, fit, nothing comes from nothing, to theological doctrines of creation from absolute nothingness. Yet as our scientific understanding has deepened, particularly through quantum physics, This seemingly straightforward concept has become increasingly complex and elusive. What exactly do we mean by nothing? Is true nothingness, the complete absence of space, time, matter, energy, fields, laws, or even potential, physically possible, or even logically coherent? When cosmologists debate whether the universe came from nothing, they often use the term in different ways than philosophers or theologians, leading to conceptual confusion. Understanding the nature of empty space and the various conceptions of nothingness is crucial for addressing the ultimate question of cosmic origins, as it clarifies what we're really asking when we wonder if the universe emerged from nothing. This exploration takes us from everyday intuitions about emptiness to the bizarre quantum reality of the vacuum and beyond, revealing that nothing might be the most complex and misunderstood concept in our quest to understand the beginning of everything. The philosophical concept of nothingness has a rich history dating back to ancient civilizations. Greek philosophers grappled extensively with the concept, often reaching dramatically different conclusions. Parmenides, in the 5th century BCE, famously argued that non-being or nothingness cannot exist. What is not cannot be thought or spoken of meaningfully, and therefore nothing can come from nothing. Democritus and the atomists proposed that reality consists of atoms moving through empty space or void, making a crucial distinction between nothing as empty space and the more absolute concept of non-existence. Aristotle rejected the possibility of a true vacuum, asserting that nature abhors a void, a principle that influenced scientific thinking for nearly 2 millennia. Eastern philosophical traditions offer different perspectives. Taoist concepts like Wu, emptiness, and Buddhist notions of shunyata, emptiness or voidness, conceived of nothingness not as mere absence but as a pregnant emptiness with creative potential. These traditions often emphasize that emptiness and form are interdependent rather than absolute opposites. Medieval philosophers across Islamic, Jewish, and Christian traditions debated whether creation ex nihilo, from nothing, was a logical necessity or contradiction. Theologians like Thomas Aquinas argued that only an omnipotent God could create something from absolute nothing, while others questioned whether even divine power could overcome the principle that nothing comes from nothing. These philosophical traditions demonstrate that nothing has never been a simple or settled concept, but rather a profound metaphysical puzzle at the heart of our understanding of existence itself. Scientific, nothing differs substantially from philosophical or absolute nothing. When physicists speak of vacuum or empty space, they refer to regions without ordinary matter but still containing fields, energy, and the fundamental structure of space-time itself. This scientific conception has evolved dramatically over centuries. The ancient and medieval understanding of a plenum, a universe completely filled with matter or ether, with no empty spaces, gave way during the scientific revolution to Newton's concept of absolute space, a fixed, immovable arena within which matter exists and moves. This Newtonian void was genuinely empty in terms of matter, but still contained absolute space and time as fundamental ingredients of reality. This view persisted until Einstein's relativity theories revolutionized our understanding, showing that space and time are not fixed and absolute, but dynamic and interrelated aspects of a four-dimensional space-time that curves in response to matter and energy. Empty space in Einstein's universe isn't merely a backdrop for physical events, but an active participant with properties like curvature and expansion. Furthermore, general relativity reveals that empty space can contain energy, the so-called cosmological constant or dark energy that drives the accelerating expansion of the universe. This evolving scientific conception demonstrates that nothing, even in its most minimal scientific sense, has never been the absolute absence of everything, but rather a state with increasingly subtle and fundamental properties revealed through advancing theoretical understanding and experimental precision. Quantum fields and virtual particles dramatically transform our understanding of empty space, revealing that the vacuum is anything but empty. According to quantum field theory, the foundational framework of modern particle physics, space is permeated by fields, mathematical structures that extend throughout space and time, representing the potential for particles to exist. Even in the absence of particles, these fields remain, fluctuating according to Heisenberg's uncertainty principle, which states that certain pairs of properties, like energy and time, cannot be simultaneously measured with perfect precision. These quantum fluctuations mean that pairs of virtual particles, particles that briefly pop into existence and then annihilate each other, continually emerge from and return to the vacuum. Though they exist too briefly to be directly observed, the effects of these virtual particles have been experimentally verified through phenomena like the Casimir effect, where closely spaced metal plates experience a small attractive force caused by differences in virtual particle populations inside and outside the gap. Another dramatic manifestation of vacuum energy appears in the Lamb shift, a small difference in energy levels in hydrogen atoms caused by interactions between electrons and virtual photons in the vacuum. These experimental confirmations demonstrate that the quantum vacuum is a seething sea of potential, constantly bubbling with ephemeral particles and energy fluctuations, a far cry from the absolute nothingness of philosophical imagination. The vacuum energy associated with quantum fields presents profound puzzles for physics. Most dramatically, in the cosmological constant problem, quantum field theory predicts that even empty space should contain enormous energy density from virtual particle fluctuations. When physicists calculate this vacuum energy density from standard quantum field theory, they find a value that exceeds astronomical observations by a staggering factor. Some calculations suggest a discrepancy of up to 120 orders of magnitude, arguably the largest disagreement between theoretical prediction and observation in the history of science. Yet astronomical observations indicate that while vacuum energy, in the form of dark energy, does exist and is driving cosmic acceleration, its value is relatively tiny. This massive discrepancy suggests either that our understanding of quantum fields is fundamentally incomplete, or that some unknown mechanism almost perfectly cancels the enormous vacuum energy predicted by quantum theory, leaving only the tiny residual we observe as dark energy. This cosmological constant problem lies at the intersection of quantum physics and general relativity, highlighting how our understanding of nothing connects directly to the deepest unsolved problems in theoretical physics. The fact that calculating the properties of empty space leads to such dramatic conflicts between our most successful physical theories demonstrates how profound and challenging the concept of nothingness becomes at fundamental scales. Can physics explain true nothingness, the complete absence of everything, including space, time, fields, and laws? This question pushes beyond operational science into metaphysical territory, as true nothingness would, by definition, lack any properties that could be measured or modeled. Some theoretical approaches attempt to address how something might emerge from a state as close to absolute nothing as can be conceived within physics. Quantum cosmological models, like those developed by Alexander Vilenkin, suggest that a closed universe could tunnel quantum mechanically from literally nothing, with the positive energy of matter precisely balanced by the negative gravitational energy, resulting in a universe with zero total energy. Edward Tryon similarly proposed that our entire universe might represent a vacuum fluctuation, appearing spontaneously with no net energy cost. These models attempt to minimize what must be assumed to exist initially, but they still presuppose quantum mechanical principles and the potential for space-time to emerge. Physicist Lawrence Krauss has argued that the quantum vacuum, though not absolutely nothing in the philosophical sense, is the closest physical analog to nothingness, and that quantum mechanics explains how our universe could emerge from this state without requiring external causation. Critics, including philosophers like David Albert, counter that quantum fields, laws, and potentials already constitute a substantial something, making claims about creation from nothing misleading when quantum fields are presumed to exist. This debate highlights the challenge of bridging scientific and philosophical concepts of nothingness and the difficulty of explaining the origin of everything, including the laws of physics themselves. The laws of physics seem to disfavor absolute nothingness, suggesting that something might be the default state of reality rather than nothing. Quantum mechanics, through the uncertainty principle, implies that truly empty space with exactly zero energy and absolutely no fluctuations cannot exist, even in principle. The laws of thermodynamics suggest that perfect order, or perfect disorder, is an idealized state never fully realized in practice. General relativity indicates that empty space can contain energy and curvature, even in the absence of matter. These principles suggest that some version of something may be inevitable, given the laws of physics as we understand them. This observation leads to a profound chicken and egg problem. Do the laws of physics prevent absolute nothingness, or does the impossibility of absolute nothingness give rise to the laws of physics? If the laws themselves are part of what exists rather than nothing, what explains their existence? Some theorists propose that mathematical consistency alone might determine which physical laws are possible, suggesting that the laws of physics represent necessary rather than contingent truths, things that couldn't have been otherwise. Others suggest that our universe's laws might be just one realization among many possibilities in a multiverse, with different regions governed by different effective laws. These approaches attempt to ground the laws of physics in principles that might transcend physical reality itself, potentially resolving the puzzle of why there are laws rather than no laws. Yet they all face the same fundamental challenge, explaining why any organizing principles exist at all, rather than absolute chaos or non-being. If space itself is something rather than nothing, with properties, structure, and energy, can nothing ever truly exist? Modern physics suggests that space is not merely an empty container, but an entity with intrinsic properties. It can curve, expand, vibrate, and contain energy even in the absence of ordinary matter. Quantum gravity approaches like string theory and loop quantum gravity go further, suggesting that space-time itself emerges from more fundamental structures, such as vibrating strings in higher dimensions or networks of quantum relationships. These approaches imply that even empty space-time represents a complex, structured something rather than absolute nothingness. Some physicists and philosophers have therefore argued that absolute nothingness may be logically impossible, a concept that sounds coherent in ordinary language but doesn't correspond to any possible physical or metaphysical state. This perspective suggests a potential answer to the ancient question, why is there something rather than nothing? Perhaps because nothing in the absolute sense isn't actually a possibility, with some form of existence being the inevitable default. Philosopher Robert Nozick explored this idea in his concept of the principle of fecundity, suggesting that existence might be more natural or less requiring of explanation than non-existence. While speculative, this approach reframes the mystery of existence, suggesting that what requires explanation is not why there is something rather than nothing, but rather why this particular something, our universe with its specific properties, exists rather than some other possible configuration of reality. The concept of a quantum vacuum as a sea of potentiality offers a middle ground between absolute nothingness and definite existence. In quantum field theory, the vacuum represents not the absence of all properties, but rather a lowest energy state, where fields exist without excitations, particles. This state contains tremendous potential. All possible particles and interactions exist as probabilities within it, ready to manifest under the right conditions. Some philosophical interpretations see parallels between this quantum potential and ancient concepts like Aristotle's notion of potentiality or the Taoist concept of wu, emptiness, as a fertile void from which all things emerge. Quantum cosmological models suggest that our entire universe, with its vast complexity of structures and phenomena, might have emerged from quantum fluctuations in a pre-existing vacuum state, with inflation magnifying these microscopic variations into cosmic-scale structures. This perspective transforms our understanding of creation, suggesting that rather than a transition from absolute nothing to definite something, cosmic origins might involve the actualization of pre-existing potentials in the quantum vacuum. The vacuum thus serves not as pure non-being, but as a kind of cosmic womb, a state of minimal but crucial structure from which greater complexity can naturally emerge through quantum processes. This quantum perspective on nothingness aligns with ancient philosophical insights, while providing a mathematically rigorous framework for understanding how complexity can arise from simplicity without requiring absolute creation ex nihilo. Different interpretations of quantum mechanics offer varying perspectives on the nature of the vacuum and its fluctuations. The Copenhagen interpretation, historically dominant in quantum physics, treats vacuum fluctuations as inherently probabilistic phenomena with no definite reality until measured. In this view, the vacuum contains not actual particles, but probability distributions describing where and when particles might be observed. The many worlds interpretation, by contrast, treats all quantum possibilities as equally real, suggesting that virtual particles popping out of the vacuum actually exist in parallel branches of reality that immediately decohere from our branch when the particles re-annihilate. Quantum field theory in curved spacetime, which attempts to combine quantum effects with general relativity, suggests that the very concept of vacuum becomes observer-dependent in curved or expanding space. What appears as empty vacuum to one observer might contain particles for another observer moving differently. These interpretational differences highlight how profoundly quantum theory has transformed our understanding of nothingness, replacing the simple intuitive concept of absence with a rich, complex, and sometimes observer-dependent notion. Despite these different interpretations, all quantum approaches agree that the vacuum contains structure, energy, and potential, a kind of proto-reality rather than absolute non-being. This convergence across interpretations suggests that, regardless of which quantum framework ultimately proves correct, absolute nothingness is likely physically impossible, with the quantum vacuum representing the closest approximation to nothing that can actually exist within our universe. The zero-energy universe hypothesis suggests a potential resolution to the puzzle of cosmic creation by proposing that the total energy of the universe exactly equals zero, with positive contributions from matter and radiation precisely balanced by negative contributions from gravitational potential energy. Pioneered by physicists including Edward Tryon and elaborated by others like Lawrence Krauss and Alexander Vilenkin, this approach suggests that a universe with zero net energy could emerge spontaneously from a quantum vacuum state without violating conservation of energy. In essence, the universe would represent a perfect bookkeeping balance with no net cost in energy terms, a cosmic free lunch. If correct, this hypothesis would partially address the ancient philosophical puzzle of why there is something rather than nothing, suggesting that the something of our universe might be energetically equivalent to nothing when all contributions are properly accounted for. The zero-energy universe concept receives support from inflationary cosmology, which suggests that the flat spatial geometry we observe, confirmed by cosmic microwave background measurements, implies a precise balance between positive and negative energy contributions. However, critics note that even if the total energy sums to zero, the emergence of structured, patterned reality from quantum vacuum still involves the existence of physical laws, fields, and potentials that themselves require explanation. The zero-energy hypothesis might explain how the universe could emerge consistently with conservation principles, but it doesn't fully resolve the deeper mystery of why the physical framework enabling such emergence exists at all. Different cultural and religious traditions have developed sophisticated concepts of nothingness that sometimes align with modern scientific understandings in surprising ways. The Buddhist concept of shunyata, emptiness, doesn't refer to a nihilistic void, but rather to the lack of independent, inherent existence in all phenomena. everything exists through interdependent relationships, rather than containing essence in isolation. This perspective resonates with quantum field theory's picture of particles as excitations in fields that permeate all space, with no fundamental separation between objects and their environment. The ancient Chinese concept of Wu, nothingness, in Taoism represents not absence, but limitless potential, the undifferentiated state from which all distinct things emerge, similar to how quantum cosmology describes the emergence of distinct particles and structures from the quantum vacuum. Western mystical traditions across Jewish, Christian, and Islamic thought developed concepts of the divine as transcending all categories, including existence and non-existence, with creation emerging not from absolute nothing, but from the ineffable divine reality beyond human conceptualization. These diverse traditions suggest that the puzzle of nothingness and emergence has engaged human thought across cultures and epochs, with pre-scientific intuitions sometimes anticipating aspects of modern physical understanding. While scientific cosmology operates independently of these religious frameworks, the resonances between ancient wisdom traditions and contemporary physics highlight how certain fundamental puzzles about existence and non-existence transcend historical and cultural boundaries, representing perennial questions at the heart of human attempts to comprehend reality's fundamental nature. The limits of human language and cognition constrain our ability to conceptualize and discuss true nothingness. Our languages evolved to describe things that exist rather than their absence, and our cognitive apparatus developed to navigate a world of objects and relationships rather than to contemplate absolute non-being. When we try to think about nothing, we inevitably picture a sort of empty container or space, a something, rather than the complete absence of everything, including space itself. The philosopher Ludwig Wittgenstein famously observed that many philosophical problems arise from the misuse of language, and the concept of absolute nothingness may exemplify this challenge. When we ask, why is there something rather than nothing, or what existed before the universe, we use linguistic constructions that subtly presuppose frameworks of existence, causality, and time, the very concepts we're trying to inquire beyond. This linguistic limitation doesn't mean the questions are meaningless, but it suggests we should be cautious about taking our intuitive understanding of terms like nothing, before, or cause too literally when approaching the frontiers of cosmology. Some philosophers, including Martin Heidegger, have attempted to develop specialized terminology and conceptual frameworks to discuss nothingness more rigorously, recognizing that everyday language may be inadequate for metaphysical inquiry at this level. Similarly, mathematical formalisms in theoretical physics may transcend the limitations of natural language, providing more precise ways to model states approaching true nothingness, even if we cannot intuitively visualize or verbally describe such states without subtle contradictions. The concept of nothing in cosmological origin theories thus proves remarkably complex and multi-layered. At minimum, we can distinguish at least 5 distinct concepts, often conflated in discussions about cosmic origins. Absolute philosophical nothing, the complete absence of everything including laws, potentials, or possibilities. Quantum vacuum nothing, a state with no particles but containing fields, energy, and quantum potential. Spatial nothing, the absence of space itself, though time or other dimensions might exist. Temporal nothing, the absence of time, though space might exist. And mathematical nothing, the null set or zero, which paradoxically has definite mathematical properties despite representing absence. When cosmologists debate whether the universe came from nothing, they typically refer to quantum vacuum nothing rather than the more absolute philosophical nothing favored in some theological arguments. This conceptual clarification doesn't resolve the mystery of ultimate origins, but it helps prevent talking past each other by distinguishing different senses of nothing that might apply in different theoretical contexts. Some approaches to quantum cosmology suggest ways the universe might have emerged from states approaching various concepts of nothing, but all such models necessarily retain some minimal structure. whether quantum fields, mathematical laws, or probability distributions, that prevents them from reaching absolute philosophical nothing. This observation suggests that the ancient philosophical principle that nothing comes from nothing, ex nihilo nihil fit, may remain valid even within modern cosmology, with the crucial qualification that the nothing that appears in our best physical theories retains structure and potential from which complexity can emerge. As we continue exploring the origin of the universe, the question of whether absolute nothingness is physically possible or ever existed becomes increasingly central. If even empty space contains fields, energy, and structure, and if quantum principles prevent the existence of a state with absolutely zero fluctuations, then perhaps the traditional framing of the cosmic origin question requires revision. Rather than asking how something emerged from absolute nothing, we might instead ask why reality takes this particular form rather than another, why these specific fields, constants, and laws govern our universe rather than alternatives. This reframing acknowledges that some form of structured existence might be inevitable, with the real puzzle being the specifics of cosmic architecture rather than existence itself. Alternatively, if we maintain that absolute metaphysical nothingness remains a coherent possibility, then the emergence of structured reality requires explanation beyond current physics, whether through multiverse scenarios where all possibilities are realized, through mathematical necessity where consistent patterns inevitably manifest, or through transcendent causation beyond the physical realm. Regardless of which approach proves most fruitful, understanding the nature of nothing and empty space represents one of the most profound challenges in our quest to comprehend cosmic origins. The journey from intuitive notions of emptiness to the complex quantum reality of the vacuum highlights how deeply our common sense concepts can be transformed by scientific inquiry, and how the most apparently simple notion, the absence of everything, might in fact be the most profound mystery in our quest to understand the beginning of everything we observe. Quantum mechanics, with its probabilistic nature and counterintuitive principles, offers perhaps our most promising framework for understanding how the universe might have emerged from a pre-existing state, or even something approaching nothingness. Developed in the early 20th century to explain phenomena at atomic and subatomic scales, quantum theory has grown into a comprehensive mathematical framework that fundamentally challenges our classical intuitions about reality. Where classical physics describes a deterministic world of definite objects with precise properties, quantum mechanics reveals a reality of probabilities, uncertainties, and interconnections that defy common sense. Applying quantum principles to the earliest moments of cosmic history suggests possibilities that would seem miraculous in a classical framework. Particles appearing spontaneously from energy fields, the universe tunneling into existence like a particle penetrating an energy barrier, or multiple universes branching from a single quantum event. If the universe did indeed emerge through quantum processes, then indeterminism, uncertainty, and probability may be woven into the very fabric of reality at its most fundamental level, transforming our understanding of both how and why the cosmos came to be. Heisenberg's uncertainty principle, formulated by Werner Heisenberg in 1927, stands as one of the most revolutionary insights in the history of physics, with profound implications for understanding cosmic origins. Unlike measurement limitations in classical physics, which can in principle be overcome with better instruments, the uncertainty principle represents a fundamental feature of reality. Certain pairs of properties, such as position and momentum, or energy and time, cannot simultaneously be known with perfect precision. This inherent uncertainty means that even in supposedly empty space, energy levels cannot remain precisely at zero for any finite time interval. Energy must fluctuate, allowing for the momentary appearance of virtual particles that pop into and out of existence. For cosmology, this principle suggests something remarkable. The vacuum state of the early universe would necessarily have contained energy fluctuations, potentially providing the seeds for cosmic structure, or even, in some theoretical frameworks, for the emergence of the universe itself. The uncertainty principle undermines the classical notion that absolute nothingness could persist indefinitely, as quantum fluctuations would inevitably disturb any perfect state of non-being. Some cosmological models propose that our entire universe might represent a large-scale manifestation of these quantum fluctuations, a statistical improbability made possible by the inherent indeterminism built into quantum reality. The quantum vacuum, the lowest energy state of quantum fields, represents one of the most profound revisions to our understanding of empty space, with direct relevance to cosmic origins. Far from being truly empty, the quantum vacuum contains fields that permeate all of space, fields that represent the potential for particles to exist rather than actual particles themselves. These fields fluctuate constantly in accordance with Heisenberg's uncertainty principle, giving rise to a dynamic, energy-laden state that some physicists describe as a sea of virtual particles. Virtual particles continuously emerge from and dissolve back into this vacuum, existing for such brief intervals that they cannot be directly observed, but nonetheless leave detectable traces through their interactions with matter and with each other. The Casimir effect provides experimental confirmation of these vacuum fluctuations, measuring the small attractive force between closely spaced metal plates caused by differences in the spectrum of virtual particles that can exist inside and outside the gap. For cosmological origins, the energy and fluctuations inherent in the quantum vacuum offer a potential starting point for universe formation, suggesting that even the nothing that might have preceded our cosmos contained the seeds of complexity within its quantum structure. Quantum fluctuations, temporary, random variations in the energy of quantum fields, play a crucial role in several leading models of cosmic origins. In the inflationary model, quantum fluctuations in the inflaton field, the field that drove exponential cosmic expansion, became magnified to cosmic scales, eventually seeding the formation of galaxies and galaxy clusters. These minute energy variations left their imprint in the cosmic microwave background as tiny temperature differences across the sky, a pattern that has been precisely measured by satellites like WMAP and Planck, providing strong evidence that quantum effects played a direct role in shaping large-scale cosmic structure. Beyond their role in seeding structure, some cosmological models propose that quantum fluctuations might have initiated the universe itself. Alexander Vilenkin's quantum cosmology model suggests that the universe could have begun as a quantum tunneling event, where space-time spontaneously emerged from a state of nothing in the physics sense, through a process analogous to quantum tunneling, in which particles can penetrate energy barriers that would be insurmountable in classical physics. These models suggest that random quantum processes might underlie the very existence of our universe, not just its detailed structure, a profound shift from deterministic creation narratives to a picture where indeterminism and probability operate at the most fundamental level of reality. Does the universe obey quantum rules at all scales, including the largest cosmological scales and the earliest moments of cosmic history? This question sits at the heart of attempts to develop a quantum theory of gravity, a framework that would unite general relativity, our best theory of space, time, and gravity, with quantum mechanics, our best theory of matter, energy, and the other fundamental forces. Currently, these two pillars of modern physics remain incompatible at a fundamental level. General relativity describes a smooth, continuous space-time fabric that curves in response to matter and energy, while quantum theory describes a reality of discrete
Imagine
quanta,
a time before
probability
anything existed.
amplitudes,
No
inherent
stars,
uncertainty.
no planets,
This
no
theoretical
light,
conflict
no
becomes
darkness,
most acute in
not even
contexts
space
involving
itself.
both strong gravity
The universe
and
we know
quantum
and live in
effects,
today was
the
once a
interior
blank
of black
canvas,
holes,
so empty
and
and
the first
silent.
fraction of a second
It was
after
almost
the
as
Big
if
Bang.
it wasn't there at
Various
all.
approaches to
But then,
quantum gravity,
in a moment we can hardly
including
fathom,
string theory,
everything changed.
loop quantum gravity,
This is the
and
story
causal
of
set
how our
theory,
universe came to life.
attempt to resolve this conflict
But here's
by
the
proposing
catch.
deeper structures
It didn't come from
which
somewhere.
both quantum
It
mechanics
came from nothing.
and general relativity
A nothingness
emerge
so
as
complete,
information
so
valid
profound
in different
that
domains.
it defies everything
While
we
we
think
currently
know
lack
about the laws of
experimental
reality.
tests for most quantum
How
gravity
did it happen?
proposals,
What
upcoming
sparked the birth
gravitational
of
wave
everything around
observatories,
us?
cosmic microwave
This journey
background
begins in the
measurements,
most
and
unimaginable
high-energy
place.
physics experiments may eventually
place where
provide
everything,
evidence for quantum
even the
effects
idea
in
of
gravity,
beginning,
potentially
exist.
revolutionizing our understanding of cosmic origins by revealing the quantum nature of space-time itself.
Imagine
Could the
a time
universe have
before
been a
anything
quantum
existed.
event?
No
Several
stars,
theoretical
no
frameworks
planets,
suggest
no
ways
light,
our universe
no
might have
darkness,
emerged
not even
through quantum
space
processes
itself.
from a
The
pre-existing
universe
state
we
or
know and
condition.
live in today
The Wheeler-DeWitt
was once
equation,
blank
a foundational
canvas,
equation
so
in quantum
empty
cosmology
and
developed by
silent.
John Wheeler
It
and
was
Bryce
almost as
DeWitt
if it
in the
wasn't there at all.
1960s. Attempts to
Then, in a
apply
moment
quantum
we can hardly
principles to the
fathom,
universe as a whole,
everything changed.
treating it as a single
This is
quantum
the story
system
of
described
how
by
our
a universal wave
came to
function.
life.
In this approach,
But here's the
the
catch.
universe doesn't
It didn't
evolve in
come from
time,
somewhere.
but rather
It
exists
came from
as a
nothing.
superposition of
A
all possible
nothingness so
configurations
complete,
of space-time
so
and matter,
profound,
with our
that it
observation of an
defies
apparently
everything we
classical,
think we know about
time-evolving
the laws
cosmos
of
emerging
reality.
from this more
How
fundamental,
did it
timeless
happen?
quantum reality.
What sparked the
Hawking and
birth of
Hartle's
everything
no-boundary
around us?
proposal builds
This
on this
journey
framework,
begins in the most
suggesting that the
unimaginable
universe's
place,
origin might
a
be
place where
analogous to
everything,
the smooth,
even
rounded
the
tip
idea
of a
of
cone,
beginning,
with no
didn't
sharp temporal
even
boundary
exist.
or beginning point that would require explanation. In their model, the dimension we experience as time emerges smoothly from a more fundamental space-time reality, with the apparent beginning of the universe representing a change in the character of dimensions rather than a true temporal boundary. These quantum cosmological models share a common theme. They replace the classical notion of cosmic creation as a singular, deterministic event with quantum processes involving probability, uncertainty, and multiple possibilities. Quantum entanglement, the phenomenon Einstein famously described as spooky action at a distance, may play a crucial role in the emergence of space, time, and cosmic structure from more fundamental quantum reality. When particles become entangled, their properties become correlated in ways that persist regardless of the distance between them, with measurements on one particle instantaneously affecting the possible measurement outcomes for its entangled partners. Some approaches to quantum gravity, particularly those based on holographic principles, propose that space-time itself might emerge from patterns of quantum entanglement among more fundamental entities. Mark van Ramsdonk and others have developed this perspective, suggesting that the connectivity of space-time, which regions connect to which others, might be determined by patterns of quantum entanglement in an underlying non-spatial reality. Applied to cosmic origins, these entanglement-based approaches suggest that the universe's beginning might represent not the creation of everything from nothing, but rather the emergence of classical space-time from a more fundamental quantum reality, where entanglement patterns organize information in ways that give rise to the appearance of space, time, and matter as we experience them. Quantum decoherence, the process by which quantum systems lose their wave-like probabilistic character and begin to behave classically, provides insight into how our apparently deterministic, macroscopic universe might emerge from quantum origins. When quantum systems interact with their environment, information about their quantum states spreads into the surrounding systems, causing quantum superpositions to effectively collapse into definite classical states from the perspective of observers embedded within that environment. Applied to cosmology, decoherence helps explain the quantum to classical trend might not be fundamental. If the universe did originate with quantum processes, decoherence would represent a crucial bridge between its quantum origins and the classical cosmos we observe, explaining how probabilistic quantum rules could give rise to an apparently deterministic universe with a definite history and structure. The relationship between quantum mechanics and time raises profound questions about cosmic beginnings. In standard quantum mechanics, time appears as an external parameter rather than a dynamical variable. The Schrödinger equation describes how quantum states evolve with respect to time, but time itself remains a classical background parameter. This treatment becomes problematic in quantum cosmology, where space-time itself should emerge from quantum principles rather than being presupposed. The Wheeler-DeWitt equation notably lacks any explicit time parameter, suggesting that at the most fundamental level, the universe might be timeless, a static quantum state encompassing all possible configurations of matter and space-time. This problem of time in quantum gravity has led to various theoretical approaches. Some suggest that time emerges as an approximate concept from more fundamental timeless reality. Others propose that certain degrees of freedom within the universe can serve as effective clocks, against which change can be measured. Applied to cosmic origins, these considerations suggest that the apparent beginning of time with the Big Bang might represent not an absolute temporal boundary, but rather the limit of applicability for our time concept. Beyond this limit, reality might exist in a form where conventional notions of before and after lose meaning. The application of quantum principles to cosmology ultimately transforms our understanding of both how and why the universe might have come into being. Where classical physics presents us with a cosmos of deterministic processes unfolding in a fixed space-time arena, quantum cosmology offers a fundamentally different picture, a universe of possibilities and probabilities, where indeterminism operates at the deepest level of reality, where space and time themselves might emerge from more fundamental quantum relationships, and where our universe might represent one actualized possibility among countless potentials inherent in quantum reality. This quantum perspective on cosmic origins doesn't eliminate the mystery of existence, but it reframes it in profound ways. Rather than asking why there is something rather than nothing, we might ask why this particular quantum configuration rather than others. Rather than seeking an absolute beginning point that would require external causation, we might explore how time itself emerges from timeless quantum reality, rendering the concept of absolute beginnings potentially meaningless. As we continue developing and testing quantum cosmological models, we may find that the counterintuitive principles that govern the subatomic world, uncertainty, superposition, entanglement, and probability, also underlie the largest scales of cosmic history, connecting the behavior of elementary particles to the origin and evolution of the entire observable universe. Perhaps the most radical transformation in our cosmic understanding has been the growing possibility that our universe may be just one among many in a vast multiverse, a concept that has evolved from speculative fringe to mainstream theoretical consideration in contemporary cosmology. This paradigm shift challenges our most fundamental assumptions about the uniqueness and totality of what we call the universe, suggesting instead that reality may be far larger, more diverse, and more complex than even our most ambitious previous cosmological models proposed. While the multiverse remains a theoretical construct rather than an observationally confirmed reality, several independent approaches in modern physics converge on this possibility, suggesting that our observable cosmos might be just one bubble, branch, or region within a much vaster and possibly infinite reality. This perspective opens new avenues for explaining cosmic origins. Rather than our universe appearing in isolation through a singular creation event, it might instead have emerged from a pre-existing multiverse structure through processes potentially governed by comprehensible physical principles. If true, the multiverse concept would represent one of the most profound expansions of our cosmic perspective, since the Copernican revolution first displaced Earth from the center of the cosmos, potentially resolving long-standing puzzles about our universe's seemingly special properties, while simultaneously raising new questions about the ultimate nature and origin of reality itself. Different multiverse theories propose varying relationships between our universe and other possible universes, with important implications for cosmic origins. The inflationary multiverse, emerging from cosmic inflation theory, suggests that our observable universe represents just one bubble or pocket within a vastly larger inflating space. In this scenario, inflation continues eternally in most regions of space, while occasionally stopping in localized areas that become pocket universes like our own, a process that has no beginning and no end, potentially generating an infinite number of universes with varying properties. The quantum multiverse, associated with the many worlds interpretation of quantum mechanics, proposes that every quantum event creates branches in reality, with all possible outcomes occurring in different branches of a universal wave function. This approach suggests our universe's particular history represents just one path through a vast landscape of possibilities, all equally real within the larger quantum reality. The brane multiverse, arising from string theory, suggests our universe might exist on a three-dimensional membrane, or brane, floating within higher dimensional space alongside other brane universes, with possible interactions between these parallel worlds through gravity or high-energy events. Cyclic multiverse models propose that our universe might undergo endless cycles of expansion and contraction, or that it might have been born from another universe through processes like black hole formation or quantum tunneling. These diverse theoretical frameworks approach the multiverse concept from different directions, yet converge on the possibility that our observable universe exists within a larger cosmic context, fundamentally changing how we conceptualize its origin. Bubble universes represent perhaps the most widely discussed multiverse scenario, emerging directly from inflationary cosmology. First developed by physicists including Alan Guth, Andrei Linde, and Alexander Vilenkin in the 1980s, eternal inflation theory suggests that once cosmic inflation begins, it continues forever in most regions of space while ending in localized pockets that become individual universes. This process resembles water boiling, with expanding space like the rising steam and pocket universes, like the bubbles forming within it. In this scenario, our observable universe, everything we can see out to approximately 46 billion light-years in all directions, would be just one bubble in an immensely larger and possibly infinite inflating space containing countless other bubble universes. Quantum fluctuations in the inflaton field, the field driving inflation, would create regions with different physical properties, potentially leading to bubbles with different physical constants, different effective laws of physics, or even different dimensions of space and time. Some bubbles might immediately collapse. Others might be inhospitable to complex structures or life, and others still might develop conditions similar to or wildly different from our own universe. If this bubble multiverse exists, our universe would be neither unique nor the first. It would be one emergence event in an eternal process that had no beginning and will have no end, fundamentally changing how we conceptualize cosmic origins. The many worlds interpretation of quantum mechanics, first proposed by Hugh Everett III in 1957, suggests another form of multiverse with profound implications for cosmic origins. This approach takes quantum theory's mathematics at face value, proposing that when quantum systems exist in superpositions of different possible states, all possibilities actually occur in different branches of reality, rather than collapsing to a single outcome. In this view, reality consists of a constantly branching wave function containing all possible outcomes of all quantum events. Applied to cosmology, this would mean that the early universe underwent all possible quantum fluctuations simultaneously in different branches, with our particular cosmic history representing just one path through a vast landscape of possibilities. The apparent fine-tuning of cosmic parameters, the precise values of physical constants that allow for complexity in life, would be explained naturally in this framework. All possible values exist in different branches, and we necessarily find ourselves in a branch compatible with our existence. Rather than our universe having a single definite history, it would exist as a superposition of all possible histories, with our observed reality emerging through decoherence, the process by which quantum systems effectively become classical through interactions with their environment. While empirically indistinguishable from other quantum interpretations regarding experimental predictions, the many worlds approach offers a fundamentally different conceptual framework for understanding cosmic origins, replacing the singular universe paradigm with a branching multiverse where all possibilities are realized. String theory landscapes provide yet another pathway to multiverse concepts. suggesting a vast ensemble of possible universes with different physical laws. String theory proposes that fundamental particles are actually tiny vibrating strings in higher dimensional space, with different vibration patterns corresponding to different particles. The mathematics of string theory requires extra spatial dimensions beyond the three we experience, with these extra dimensions compactified or curled up so tightly they remain undetectable in everyday experience. Crucially, these extra dimensions can be compactified in an enormous number of different ways. By some estimates, around 10 to the 500th power distinct configurations, with each configuration producing different effective physical laws and constants in the resulting four-dimensional spacetime. This vast landscape of possible physical configurations suggests a corresponding landscape of possible universes, each with different properties. Cosmological processes like eternal inflation could potentially actualize this landscape, producing a multiverse where different regions manifest different string theory solutions with different physics. If this scenario is correct, our universe would represent just one valley in an immense landscape of possibilities, with its particular physical constants and laws, reflecting which valley we happen to occupy, rather than representing unique or inevitable values. This perspective has profound implications for cosmic origins, suggesting that the apparent fine-tuning of our universe's parameters might reflect selection effects in a vast ensemble, rather than requiring a unique explanation for precisely these values. Could another universe have birthed ours? Several theoretical frameworks suggest mechanisms by which universes might generate new universes, creating a reproductive or evolutionary process at the cosmic scale. Lee Smolin's cosmic natural selection hypothesis proposes that black holes might serve as the reproductive mechanism of universes, with each black hole creating a new universe through its singularity, with slightly modified physical parameters compared to its parent universe. In this speculative but mathematically grounded scenario, universes that produce many black holes would have more offspring, leading to a kind of cosmological evolution favoring universes with physical parameters conducive to black hole formation, which, interestingly, also tend to favor complex chemistry and potentially life. Other proposals suggest quantum tunneling events, higher dimensional brane collisions, or fluctuations in eternal inflation might enable one universe to spawn another. These cosmological reproduction models offer a potential explanation for our universe's apparently special properties. Rather than being created ex nihilo with arbitrary parameters, our cosmos might have inherited its basic properties from a parent universe through processes that favor certain parameter values over others. If true, this would suggest our universe has a cosmic lineage stretching back through previous universes, potentially ad infinitum, fundamentally changing the question of ultimate origins from why is there something rather than nothing to how does the process of cosmic reproduction work and has it been eternal? Are black holes portals to new universes? This question, once firmly in the realm of science fiction, has gained theoretical support from several directions in contemporary physics. General relativity suggests that matter collapsing into a black hole encounters a singularity, a point where density becomes infinite and known physics breaks down. However, quantum effects likely become dominant near this singularity, potentially transforming it from a true ending point to a bounce or transition. Theoretical physicist Roger Penrose has proposed that the immense but finite densities in black hole interiors might create conditions analogous to the Big Bang, potentially spawning new expanding spacetimes disconnected from our own universe. Similarly, some loop quantum cosmology models suggest that extreme gravitational collapse could bounce into expansion through quantum repulsion effects, creating a new expanding region of spacetime. If these theories are correct, the millions of black holes in our observable universe might each be creating new universes, invisible and inaccessible to us, but nevertheless real. This scenario, would fundamentally transform our understanding of cosmic origins and evolution, suggesting that universes form a vast branching tree of parent-child relationships, with black holes serving as the reproductive mechanism. Our own universe, in this picture, would be one branch in this cosmic tree, perhaps originating from a black hole in another universe, a perspective that replaces the traditional question of first beginnings with an ongoing process of cosmic reproduction that might have no beginning or end. The cosmic egg theory, the idea that our universe might have emerged from a previous cosmic phase through a transformative process, has appeared in various forms throughout human history, from ancient mythologies to modern scientific cosmologies. In contemporary physics, several models propose that our expanding universe might have emerged from a pre-existing state through processes like quantum tunneling, phase transitions, or bounces from previous contractions. Paul Steinhardt and Neil Turock's ekpyrotic and cyclic universe models, inspired by string theory, suggest that our universe exists on a brane, a membrane-like structure in higher dimensions that periodically collides with another parallel brane, with each collision initiating a new phase of cosmic expansion resembling a Big Bang. Roger Penrose's conformal cyclic cosmology proposes that the infinitely expanded empty state of a previous universe becomes mathematically equivalent to the extremely compressed state of a new universe's beginning, creating an endless cycle of universes connected by conformal transformations. These scientific cosmic egg theories differ from their mythological predecessors by proposing specific mathematical mechanisms for the transition between cosmic phases, potentially subject to empirical testing through astronomical observations. If any such model proves correct, our universe would not have emerged from absolute nothingness, but rather from a transformed previous state, fundamentally changing how we conceptualize the beginning of our cosmic history. Can we ever prove or disprove the multiverse? This profound question sits at the intersection of science, philosophy, and the limits of knowledge. Critics argue that since other universes would by definition lie beyond our observable horizon, the multiverse concept might be inherently untestable and therefore outside the bounds of scientific inquiry. Proponents counter that while we cannot directly observe other universes, multiverse theories make testable predictions about our own universe's properties. For instance, if our universe formed through quantum tunneling from a parent universe, specific patterns might appear in the cosmic microwave background radiation. If eternal inflation occurs, we might observe signatures of collisions between our bubble universe and others. If cosmic natural selection operates, we would expect our universe's parameters to be optimized for black hole production. More broadly, if the multiverse exists, our universe's parameters would likely be typical among the subset capable of producing observers rather than having uniquely special values, providing a potential statistical test. Additionally, the multiverse concept gains credibility not primarily through direct observation, but through its emergence as a prediction from independently motivated theories, inflation, quantum mechanics, and string theory, that have explanatory power in other domains. While definitive proof may remain elusive, the accumulation of circumstantial evidence and theoretical consistency might eventually establish the multiverse as the most reasonable explanation for our universe's observed properties, similar to how continental drift was accepted before direct observation became possible. The anthropic principle, the observation that what we can observe about the universe is necessarily constrained by our existence as observers, takes on special significance in multiverse theories. In its weak form, the anthropic principle merely notes that our observations are inevitably biased toward conditions compatible with our existence. We can only observe universes or regions where observers can evolve. In its strong form, it makes the more controversial claim that the universe must have properties that allow for observers. If the multiverse exists with regions having widely varying physical properties, the anthropic principle provides a natural explanation for our universe's apparently fine-tuned parameters without requiring design or extraordinary cosmic coincidence. We observe these particular values for physical constants, not because they're unique or inevitable, but because we could only evolve in a universe with life-compatible parameters. This perspective transforms apparent fine-tuning from a puzzle requiring explanation into an expected selection effect. Out of the vast ensemble of possible universes, we necessarily find ourselves in one compatible with our existence, regardless of how rare such universes might be within the larger multiverse. While critics argue that anthropic reasoning lacks predictive power and might prematurely end the search for deeper explanations, proponents maintain that it represents a logical approach to understanding our cosmic circumstances when the possibility of multiple universes with different properties is taken seriously. The multiverse concept raises profound philosophical questions about the nature of reality, explanation, and scientific understanding. If our universe is one among many, what constitutes a complete explanation of reality? Is the existence of the multiverse itself a brute fact requiring no further explanation? Or does it merely push the question of ultimate origins to a higher level? Does the vastness and diversity of the multiverse enhance our understanding of reality or diminish it by suggesting our observable universe's specific properties are merely accidental rather than necessary? These questions connect to ancient philosophical debates about necessity versus contingency, simplicity versus complexity and explanation, and the limits of human knowledge. Some philosophers argue that multiverse theories violate Occam's razor by needlessly multiplying entities beyond what's required to explain observations. Others counter that the multiverse actually represents the simplest explanation when considering the full range of observations, including apparent fine-tuning. The multiverse concept also transforms how we think about laws of physics. Rather than being universal and immutable dictates, laws might be more like local bylaws, varying across the broader multiverse while maintaining consistency within our observable region. These philosophical dimensions of multiverse theories highlight how cosmic origin questions inevitably transcend purely technical scientific considerations, touching on fundamental questions about the nature of explanation and the limits of human understanding. The mathematical multiverse, proposed by physicist Max Tegmark, represents perhaps the most expansive multiverse concept, suggesting that all mathematically consistent structures exist physically somewhere in the multiverse. In this hypothesis, physical reality isn't merely described by mathematics, it is mathematics, with our universe representing one mathematical structure amongst countless others. This perspective organizes multiverse concepts into hierarchical levels. Level 1 contains regions beyond our cosmic horizon, but with the same physical laws. Level 2 includes regions with different physical constants emerging from processes like eternal inflation. Level 3 encompasses the many worlds of quantum mechanics, and Level 4 comprises all mathematically consistent structures. This mathematical multiverse offers a potential ultimate explanation for existence itself. Mathematical consistency alone would determine what can exist, with no further explanation needed for why these mathematical structures are physically realized. It suggests that our universe exists not because it was uniquely created, but because the mathematical structure corresponding to our physical laws is logically consistent and therefore real within this grand mathematical multiverse. While highly speculative and perhaps untestable even in principle, the mathematical multiverse represents a fascinating attempt to ground the ultimate question of existence in principles of logical necessity rather than contingent physical processes, potentially resolving the ancient puzzle of why there is something rather than nothing by suggesting that nothing might be logically impossible or mathematically inconsistent. Religious and spiritual perspectives on the multiverse vary widely, with some traditions finding resonance with their cosmologies, while others see conflict. Many Eastern traditions, including certain schools of Hinduism and Buddhism, have long embraced concepts resembling the multiverse. The Hindu concept of Brahman manifesting countless worlds, or Buddhist cosmology with its multiple realms of existence and endless cycles of universes. These traditions often find modern multiverse theories compatible with their ancient wisdom. Western monotheistic traditions have more varied responses. Some theologians see the multiverse as diminishing the specialness of creation and humanity's place within it, while others argue that an infinitely creative deity would naturally create multiple universes rather than just one. Still others suggest that the multiverse, if it exists, would simply represent God's chosen mechanism for creation, similar to how evolutionary theory provides the mechanism for biological diversity. Indigenous traditions often embrace multiplicity in their cosmologies, with many layers of reality and multiple worlds. These diverse perspectives remind us that questions about cosmic origins and multiple universes have engaged human imagination across cultures and throughout history, long before modern scientific formulations. While science approaches these questions through mathematics, observation, and testable theories, religious and spiritual traditions offer complementary perspectives on the meaning and purpose of existence within a potentially vast multiverse. Questions that transcend purely empirical investigation while remaining relevant to our understanding of our place in the cosmos. If our universe did emerge from another universe or a larger multiverse structure, what implications would this have for our understanding of cosmic origins? Rather than a singular beginning from nothing, we might envision our universe as one link in a vast causal chain extending beyond our observable reality. Our cosmic beginning would represent not an absolute starting point, but a transition or transformation within a larger and possibly eternal process. The apparent fine-tuning of physical constants would find natural explanation as the result of selection effects or cosmic evolution, rather than requiring extraordinary coincidence or design. The scope of reality would vastly exceed our observable universe, potentially including regions with entirely different physical laws, dimensions, or structures beyond our comprehension. While not eliminating the question of ultimate origins entirely, one could still ask why the multiverse exists at all. This perspective would transform our understanding of our own universe's beginning, embedding it within a comprehensible natural process rather than treating it as a singular event requiring exceptional explanation. The multiverse concept thus represents not merely an expansion of our cosmic horizon, but a fundamental reconceptualization of what it means for a universe to begin, replacing the traditional ex nihilo creation narrative with an ongoing process of cosmic emergence, evolution, and transformation that might have no ultimate beginning or end. As we continue exploring the question of cosmic origins, the multiverse concept offers a profound expansion of our cosmological perspective, one that doesn't eliminate the mystery of existence, but transforms how we conceptualize it. Whether through eternal inflation, quantum branching, string theory landscapes, black hole reproduction, or mathematical necessity, multiverse theories suggest that reality may be far vaster, more diverse, and more complex than our traditional cosmic models envisioned. If our universe did indeed emerge from another universe or a larger multiverse structure, then its apparent beginning would represent not an absolute starting point, but a transition within an ongoing process that might have no ultimate beginning or end. While definitive evidence for the multiverse remains elusive, the convergence of multiple theoretical approaches on this possibility suggests that our cosmic horizon may extend far beyond what we can directly observe. A humbling, yet exhilarating perspective that continues the Copernican tradition of displacing humanity from the center of the cosmos, while simultaneously revealing a reality more grand and intricate than we previously imagined. As we develop more sophisticated theoretical frameworks and observational techniques, we may eventually find compelling evidence for these broader cosmic contexts, potentially resolving long-standing puzzles about our universe's properties while revealing new mysteries about the ultimate nature and origin of reality itself. Throughout human history, perhaps no question has prompted more profound contemplation than whether our universe requires a creator or first cause. This question bridges the domains of philosophy, theology, and cosmology, touching on fundamental puzzles about existence, causality, and the limits of natural explanation. The traditional philosophical argument for a first cause, dating back to Aristotle and developed by medieval thinkers like Thomas Aquinas, suggests that every effect requires a cause. And since infinite causal chains seem logically problematic, there must be a first uncaused cause that initiated everything. Modern cosmology has transformed this ancient debate by providing scientific models of cosmic origins that potentially explain the universe's beginning through natural processes, raising the question of whether these explanations eliminate the need for a creator or merely push the question back a step. The question of a first cause connects directly to our exploration of cosmic origins, asking whether the beginning of our universe represents the ultimate starting point of all reality, or merely one transition within a larger framework. The philosophical debate about whether every effect needs a cause has ancient roots and remains relevant to modern cosmological questions. Aristotle's concept of the unmoved mover represented an early attempt to resolve the logical problems inherent in causal chains, proposing a first cause that initiates motion without itself being moved. Medieval philosophers developed sophisticated versions of this argument, with thinkers like Al-Ghazali, Maimonides, and Thomas Aquinas proposing that the contingent nature of the physical world necessitates a necessary being as its ultimate cause. The principle that nothing comes from nothing, accepted across diverse philosophical traditions, seemed to demand that something eternal and self-existent must underlie the existence of contingent reality. Modern philosophical approaches have scrutinized these traditional arguments. Some philosophers argue that the principle of sufficient reason, the idea that everything must have an explanation, logically requires a necessary first cause. Others contend that certain facts might simply be brute realities, requiring no further explanation. Contemporary philosophical discussions often focus on whether the concept of causation even applies meaningfully to the universe as a whole, since causation is typically understood as a relationship within the universe, rather than applicable to its totality. Does time need a beginning? This question has profound implications for whether a first cause is necessary. Traditional arguments for a creator often presuppose that time must have a beginning, reasoning that an infinite past would entail an infinite regression of causes. In classical theology, Augustine proposed that God created time itself along with the universe, placing the creator outside temporal sequence altogether, a perspective that avoids the problem of what happened before creation by suggesting there was no before in any temporal sense. Modern physics has transformed this discussion through Einstein's theories of relativity, which reveal time as an integrated dimension of space-time rather than an absolute flow. General relativity suggests that time itself might have begun with the Big Bang, potentially eliminating the question of what came before. However, various cosmological models propose alternatives. Cyclic universe theories suggest our Big Bang might be one in an endless sequence. Eternal inflation models describe an ever-expanding multiverse without beginning or end, and quantum approaches suggest time emerges from a more fundamental, timeless reality. The possibility of eternal time doesn't necessarily eliminate the need for a first cause. One could still ask why this eternal process exists rather than nothing, but it does transform the nature of the question. Self-creating universe theories attempt to explain cosmic origins without invoking an external creator by suggesting the universe might somehow cause its own existence. Various theoretical approaches attempt to address this apparent paradox. Quantum cosmological models propose that closed time-like loops, or retrocausal quantum effects, might allow the universe to be self-causing in a non-temporal sense. John Wheeler's participatory anthropic principle suggests a form of bootstrap causality, where observers emerging in the universe's future somehow participate in actualizing its past quantum state. Other perspectives suggest the question might be fundamentally misconceived. Perhaps the universe simply exists as a brute fact requiring no sole explanation. Critics argue that all such self-causation theories ultimately fail because they must presuppose the existence of something: quantum fields, physical laws, probability distributions, to explain the emergence of the universe, thereby not truly explaining existence from absolutely nothing. These approaches highlight the profound difficulties in conceptualizing how anything, including the universe, could cause itself, a puzzle that continues to challenge both scientific cosmology and philosophical reasoning about ultimate origins. Can physics explain the cause of the universe without invoking something beyond physics? Multiple approaches in theoretical physics attempt to provide naturalistic explanations for cosmic origins. Quantum cosmological models suggest the universe might have emerged through quantum tunneling from a pre-existing state. Eternal inflation theories describe an ever-expanding multiverse that continuously generates new universes. String theory and quantum gravity approaches propose that space-time itself emerges from more fundamental structures. Each of these approaches pushes the causal boundary further back, potentially providing explanations for the Big Bang in terms of prior or more fundamental physical processes. However, critics argue that all such physical explanations inevitably presuppose something: quantum fields, physical laws, mathematical structures whose existence itself requires explanation. Even explanations that eliminate the need for a temporal beginning point still face the question of why these fundamental physical processes or principles exist at all, why there are quantum fields rather than nothing, or why these particular laws govern reality rather than others. This limitation suggests that while physics may increasingly explain cosmic origins in terms of natural processes, certain aspects of the first cause question might lie beyond the domain of empirical science. The problem of infinite regress haunts discussions of cosmic origins and first causes. If everything requires a cause, what caused the first cause? This chain of questioning seems to continue indefinitely, leading to three possible resolutions: an infinite causal chain extending backward without beginning, a circular causal chain, or a first uncaused cause that terminates the regress. Traditional theological arguments generally adopt the third approach, proposing God as the uncaused first cause, whose nature is fundamentally different from contingent physical reality. Naturalistic approaches face similar logical challenges. If quantum fluctuations caused the universe, what caused the quantum fields? If physical laws governed cosmic origins, what explains the existence of those laws? Some philosophers propose that the regress might terminate in facts that are simply brute, realities that have no further explanation. Others suggest that certain types of explanations, particularly those involving necessary mathematical structures, might be self-explanatory. These diverse approaches highlight how the infinite regress problem pushes both theological and naturalistic explanations toward postulating something that exists without external cause, whether described as God, fundamental physical laws, mathematical necessity, or brute reality. Religious and spiritual traditions across cultures have developed diverse perspectives on the first cause question. Traditional monotheistic frameworks describe God as eternal, necessary, and self-existent, the ground of all being, who creates freely rather than through necessity and exists outside time. Eastern traditions offer different approaches. Certain Hindu philosophical schools describe Brahman as the fundamental reality from which the cosmos manifests. Buddhist traditions generally avoid speculation about first causes, and Taoist perspectives often emphasize the spontaneous emergence of reality without requiring an intentional creator. Indigenous spiritual traditions frequently describe cosmic origins through narratives of world formation from pre-existing chaos rather than creation from absolute nothing. While differing dramatically in their specific cosmologies, these diverse traditions converge on recognizing the profound mystery of existence and the limits of human comprehension when addressing ultimate origins. Modern scientific cosmology has transformed but not eliminated questions about first causes. The Big Bang theory remains silent about the absolute origin of the matter, energy, space-time, and laws, that participated in this expansion. Inflationary models still require initial conditions and an inflaton field whose existence raises further questions. Quantum cosmological approaches presuppose quantum fields and laws that themselves require explanation. Each scientific advance seems to push the causal boundary further back without eliminating the fundamental question of why anything exists at all. Some scientists argue that certain questions, particularly why is there something rather than nothing, may lie permanently beyond scientific investigation. Others maintain that future theoretical developments might eventually provide scientific answers to these seemingly metaphysical questions. These ongoing discussions demonstrate how modern cosmology has refined and reshaped ancient questions about first causes without rendering them obsolete. Does the universe show evidence of design that might suggest a creator? The remarkable precision of fundamental constants, including the strength of gravity, the mass of elementary particles, and the cosmological constant, appears calibrated to allow for complexity and life. This observation has three main interpretations. It might indicate purposeful design by a creator. It might result from a multiverse where all possible parameter values exist in different regions, with observers necessarily finding themselves in life-compatible regions, the anthropic explanation. Or it might eventually be explained by a more fundamental theory that demonstrates why these particular values are mathematically necessary. Beyond parameter fine-tuning, some argue that the mathematical intelligibility of the universe, the emergence of consciousness, and the existence of natural laws themselves suggest a mind behind cosmic order. Others counter that natural selection, both at biological and potentially cosmological scales, could explain apparent design without requiring a designer. This debate highlights how evidence for or against a creator depends not only on empirical observations, but on the interpretive frameworks through which we understand them. The relationship between science and theology in addressing cosmic origins continues to evolve beyond simplistic conflict narratives toward more nuanced dialogue. Rather than competing explanations for the same phenomena, science and theology might address different aspects of reality or different types of questions. Science focusing on mechanisms and proximate causes through empirical investigation, theology addressing questions of ultimate meaning, purpose, and existence that transcend empirical methods. Some scholars propose that the first cause question involves both scientific and theological dimensions, with empirical cosmology progressively explaining natural mechanisms while leaving open deeper questions about why natural laws exist and why they take the particular form they do. Others suggest that theological and scientific approaches might eventually converge on similar concepts. The God of the philosophers, described in terms of necessary being, might not differ fundamentally from what physicists describe as the fundamental laws from which all reality emerges, despite the different terminologies involved. As we consider whether the universe requires a creator or first cause, we confront not only empirical questions about cosmic origins, but deeper puzzles about the nature of explanation itself. What constitutes a satisfying explanation for why anything exists at all? Must every explanation invoke something more fundamental, leading to infinite regress, or can some realities be self-explanatory? Can scientific explanations account for the existence of the framework within which science operates? Or do certain questions necessarily transcend empirical methods? The first cause question thus connects directly to the limits of human knowledge and understanding. Whether regarding ultimate origins we face merely practical limitations that future scientific developments might overcome, or fundamental limitations built into the structure of human cognition and the nature of reality itself. Whether through theological concepts of divine creation, philosophical notions of necessary being, or scientific models of emergent complexity from fundamental laws, all approaches to cosmic origins eventually confront the profound mystery of existence itself. Why there is something rather than nothing, and why this particular something rather than another. Time ranks among the most familiar yet mysterious aspects of our reality, We experience its flow continuously, yet its fundamental nature remains profoundly puzzling. While we intuitively understand time as an absolute universal flow from past to future, modern physics has transformed this simple picture, revealing time to be far more complex and potentially less fundamental than our everyday experience suggests. Einstein's theories of relativity demonstrated that time is not absolute, but relative, flowing at different rates depending on gravity and relative motion. Quantum mechanics further complicates our understanding with phenomena like entanglement that seem to transcend normal temporal ordering. These revolutionary insights have led some physicists and philosophers to suggest that time as we experience it might be emergent rather than fundamental, a useful approximation or subjective experience rather than a basic feature of reality at its deepest level. This possibility raises profound questions about cosmic origins. If time itself is not fundamental, could the universe in some sense have always existed, even without an infinite temporal past? Might the very question of when the universe began presuppose a temporal framework that breaks down at the fundamental level of reality? These considerations suggest that our quest to understand whether there was ever truly nothing might require us to reconsider not just our understanding of nothing, but also our understanding of ever, the temporal framework within which we conceptualize beginnings and endings. Einstein's theories of relativity revolutionized our understanding of time, revealing it to be intimately connected with space in a four-dimensional fabric called spacetime. Special relativity, published in 1905, demonstrated that time passes differently for observers in relative motion, with no privileged reference frame that could claim to measure true time. The famous twin paradox illustrates this principle. An astronaut traveling at near light speed would experience less time passing than their earthbound twin, returning to find their sibling aged more, a prediction confirmed by precise atomic clocks on high-speed aircraft. General relativity, published a decade later, further revealed that gravity affects time's passage, with clocks running slower in stronger gravitational fields, an effect now routinely accounted for in GPS satellite calculations. These theories overthrew the Newtonian concept of absolute time flowing uniformly throughout the universe, replacing it with a more flexible space-time that curves, stretches, and even breaks down in extreme conditions like black hole singularities and possibly the Big Bang itself. Crucially for cosmology, general relativity suggests that time likely began with the Big Bang, not in the sense that something happened before time, but rather that the temporal dimension itself emerged with the beginning of cosmic expansion, similar to how the surface of the Earth has no beginning point despite being finite. This relativistic understanding of time transforms discussions of cosmic beginnings by suggesting that asking what existed before the Big Bang might be as meaningless as asking what lies north of the North Pole, a question whose structure presupposes a dimension extending beyond its natural boundary. Does time exist beyond human perception, or is it in some sense a construct of consciousness? Philosophers have long debated whether time's passage is an objective feature of reality or a subjective experience created by our minds. Presentism, the view that only the present moment truly exists, with past and future being in some sense less real, contrasts with eternalism, which holds that all moments in time are equally real, with the apparent flow from past to future being a psychological rather than physical phenomenon. Some philosophers, including J. M. E. McTaggart in his famous 1908 paper, The Unreality of Time, have argued that time's passage involves logical contradictions suggesting it cannot be fundamentally real. Others, like Henry Bergson, emphasize the distinction between measurable clock time and the subjective duration we experience through consciousness. Modern neuroscience offers insights into how the brain constructs our temporal experience, showing how neural processes create our perception of time's flow, sometimes distorting it dramatically during altered states of consciousness or extreme events. Physicist Julian Barber has proposed a radical, timeless physics in which reality consists fundamentally of configurations, which he calls nows. without temporal connections between them, with the appearance of time emerging from the relationships among these states. These perspectives suggest that while time as measured by clocks certainly corresponds to physical processes, our intuitive sense of time's flow, the sharp distinction between past, present, and future, and the feeling of movement through time, might be a construction of consciousness rather than a fundamental feature of physical reality. For cosmology, this raises the possibility that questions about the universe's beginning presuppose a temporal framework that might be more limited than we typically assume. The arrow of time, the consistent direction of processes from past to future, presents one of the most profound puzzles in physics. While the fundamental laws of physics are almost entirely time-symmetric, working equally well forward or backward, our experienced reality shows a decisive asymmetry. Eggs break but don't unbreak. Coffee cools but doesn't spontaneously heat up. And we remember the past but not the future. This temporal asymmetry is typically explained through thermodynamics, particularly the second law, which states that the total entropy, roughly disorder, of an isolated system never decreases over time. Physicist Ludwig Boltzmann connected this law to probability, showing that systems naturally evolve from less probable ordered states to more probable disordered states simply through random molecular motions. This thermodynamic arrow of time raises a cosmic puzzle. If entropy always increases, why was the early universe in such a remarkably low entropy state? The uniform, hot plasma of the early cosmos represents an extraordinarily unlikely configuration if selected randomly, yet this initial low entropy established the thermodynamic conditions necessary for all subsequent cosmic evolution, including the possibility of life. Some theorists, including Roger Penrose, suggest that explaining this past hypothesis, the universe's initially low entropy, represents one of the greatest unsolved problems in physics, potentially requiring new physical principles beyond current understanding. Others propose that entropy should be understood in terms of gravitational degrees of freedom, with the apparently uniform early universe actually representing high gravitational entropy that decreases as matter clumps into stars and galaxies. These ongoing debates about entropy and the arrow of time demonstrate that understanding time's fundamental nature remains essential for resolving questions about cosmic origins and evolution. The steady-state theory, a major rival to the Big Bang model during the mid-20th century, proposed that the universe has existed eternally without a beginning, maintaining the same average density and appearance despite continuous expansion. Developed by Fred Hoyle, Thomas Gold, and Hermann Bondi in 1948, this theory suggested that as galaxies move apart due to cosmic expansion, new matter continuously appears in the gaps between them, maintaining constant cosmic density over infinite time. This model avoided the philosophical complications of a universe with a beginning by proposing an eternal cosmos in a state of continuous creation. The steady-state theory initially attracted significant scientific support because it eliminated the need to explain an apparent cosmic beginning and aligned with the philosophical principle that the universe should appear the same to observers at all times, the perfect cosmological principle. However, multiple lines of evidence eventually falsified this model. The discovery of the cosmic microwave background radiation in 1965 provided strong evidence for a hot, dense, early state. Observations of distant galaxies revealed cosmic evolution incompatible with a steady-state universe, and measurements of cosmic elemental abundances matched the predictions of Big Bang nucleosynthesis rather than continuous creation. While the original steady-state theory has been abandoned, its central philosophical impulse, seeking a universe without an absolute beginning, persists in various contemporary cosmological models, including eternal inflation scenarios, cyclic universe theories, and models where quantum effects prevent the classical singularity at the Big Bang. These approaches continue the quest for a universe that, while obviously evolving over time, might in some deeper sense be eternal or beginningless rather than having emerged from absolute nothing at a specific moment. Does time emerge from deeper physical laws, rather than existing as a fundamental feature of reality? Several approaches in theoretical physics suggest this possibility. In quantum gravity theories, which attempt to reconcile quantum mechanics with general relativity, time often appears as an emergent rather than fundamental phenomenon. The Wheeler-DeWitt equation, a foundational equation in canonical quantum gravity, notably lacks any time parameter, describing a timeless universe where nothing evolves. Similarly, some approaches to string theory suggest that space-time itself emerges from more fundamental mathematical structures like matrices or entanglement patterns. Physicist Sean Carroll describes this perspective. Time may be purely emergent in the sense that we have a timeless fundamental description, but need a concept of time to make sense of the macroscopic world. Loop quantum cosmology, a theory applying quantum principles to the entire universe, suggests that what appears as the Big Bang singularity in classical models might actually be a bounce from a previous contracting phase, with time extending before the apparent beginning but behaving very differently under extreme quantum gravitational conditions. Causal set theory proposes that space-time emerges from more fundamental discrete causal relationships, with time's apparent flow reflecting the growth of this causal network. These diverse approaches suggest that time, as we understand it, might not be a basic feature of reality's deepest level, but rather a useful description that emerges under certain conditions, similar to how properties like temperature emerge from molecular motion without being fundamental properties of individual particles. This perspective transforms questions about whether the universe had a beginning in time by suggesting that time itself might emerge from a deeper reality where temporal concepts as we understand them might not apply. The block universe concept, emerging from Einstein's relativity theories, suggests that past, present, and future exist equally as part of a four-dimensional space-time block, rather than flowing from one to another. In this view, championed by physicists like Hermann Weyl and philosophers like Hilary Putnam, time does not pass in any objective sense. The feeling of now, moving from past to future, represents a subjective perspective rather than a physical reality. Einstein himself expressed this view, writing to console the family of his deceased friend Michel Besso. "Now he has departed from this strange world a little ahead of me. That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion." The block universe perspective suggests that reality should be understood as a four-dimensional whole, rather than as three-dimensional space evolving through time, with all moments existing timelessly like pages in a book. This view aligns mathematically with relativity's treatment of time as a dimension similar to space, particularly in its elimination of any universal now moment that would be simultaneously present for all observers. Critics argue that the block universe fails to account for our experience of time's passage and the apparent openness of the future compared to the fixed past. Some theorists propose modified versions where the now represents an objective feature moving through the space-time block, or where the block itself grows as the future becomes determined. These debates highlight how profoundly relativity has transformed our understanding of time, suggesting that the temporal framework within which we naturally conceptualize cosmic beginnings may itself require reconceptualization. Various cyclic universe models propose that our cosmos might undergo endless cycles of expansion and contraction, avoiding an absolute beginning while incorporating the evidence for cosmic evolution. Early cyclic models, developed by physicists like Richard Tolman in the 1930s, suggested that the universe would eventually recollapse under gravity's influence, leading to a big crunch, followed by another big bang. However, these simple models face challenges. Entropy would increase with each cycle, making each subsequent universe less ordered, and observations indicating accelerating cosmic expansion suggested the universe would expand forever rather than recollapse. More sophisticated cyclic models have addressed these challenges. Paul Steinhardt and Neil Turock's ekpyrotic scenario developed in the early 2000s, proposes that our universe exists on a brane in higher dimensional space that periodically collides with another brane, with each collision triggering a new cosmic expansion phase. Roger Penrose's conformal cyclic cosmology suggests that the infinitely expanded, empty state of a future universe becomes mathematically equivalent to the extremely compressed state of a new universe's beginning, creating endless cycles connected through conformal transformations with a natural reset of entropy at each transition. Loop quantum cosmology models propose that quantum gravitational effects would cause a contracting universe to bounce, rather than reaching a true singularity, initiating a new expansion phase. These diverse cyclic approaches share a common philosophical impulse, avoiding an absolute cosmic beginning while accounting for the observed features of our expanding universe. They suggest that what appears as the beginning of time in conventional Big Bang models might instead represent a transition within a much longer or even eternal cosmic process. Imaginary time, a mathematical concept introduced by Stephen Hawking and James Hartle in their no-boundary proposal for quantum cosmology, offers another perspective on whether the universe had a beginning. In standard mathematics, imaginary numbers involve the square root of negative numbers, extending normal number concepts in useful ways. Hawking and Hartle applied this approach to time in early universe cosmology, showing that by treating time as an imaginary rather than real quantity in certain equations, the apparent singularity at the beginning of the universe could be eliminated. In this framework, asking about the beginning of time becomes similar to asking about the edge of the Earth's surface, a question based on a misconception, since a sphere has no boundary despite being finite. As Hawking explained, the universe would be completely self-contained and not affected by anything outside itself. It would neither be created nor destroyed. It would just be. When translated back to conventional time, this model still describes an expanding universe like the standard Big Bang model, but without a singular beginning point requiring explanation. While largely a mathematical technique, rather than a claim about time actually being imaginary in any experiential sense, this approach highlights how the apparent beginning of time might represent a boundary in our mathematical description rather than a genuine starting point in physical reality. The no-boundary proposal suggests that the traditional concept of a cosmic beginning at a specific moment may need reconsideration, not because the universe has existed through infinite time, but because time itself might be more complex and bounded than our intuitive understanding suggests. Could the universe be beginningless in a deeper sense, despite the evidence for cosmic evolution over approximately 14 billion years? Modern cosmological models offer several possibilities for universe without an absolute beginning. Eternal inflation suggests that while our observable universe began from a hot, dense state, the larger multiverse within which it exists may be eternal, continuously generating new pocket universes without beginning or end. Quantum cosmology approaches suggest that what appears as a beginning singularity in classical general relativity might be eliminated when quantum effects are properly considered, potentially revealing a pre-Big Bang phase, or a more fundamental description where conventional temporal concepts break down. The concept of causally disconnected regions suggests that what we call the universe, our observable cosmic region, might be just one patch within a much larger reality, with questions about the totality potentially being conceptually different from questions about our observable region. Some philosophical approaches propose that the very concept of an absolute beginning might reflect limitations in human temporal thinking rather than a feature of reality itself. Perhaps existence in some form is necessary rather than contingent, with the apparent beginning of our specific cosmic configuration representing a transition within a broader framework that itself has no beginning. These diverse approaches suggest that while the Big Bang certainly occurred approximately 14 billion years ago as a transformative cosmic event, it might not represent an absolute beginning of all reality, but rather a transition within a deeper framework, expanding our cosmic perspective beyond the temporal boundaries that initially seemed to define our universe's limits. The interplay between quantum mechanics and cosmic time raises profound questions about determinism, causality, and whether the future in some sense already exists. Traditional interpretations of quantum mechanics involve probabilistic rather than deterministic processes, with future states not fully determined by present conditions. This quantum indeterminism seems to align with our intuitive sense of an open future that is not yet fixed. However, other interpretations of quantum mechanics, including the many worlds interpretation and certain hidden variable theories, restore determinism at the cost of other intuitive features. The block universe perspective suggested by relativity implies that future events already exist in some sense, even if we cannot access information about them, creating tension with quantum indeterminism. Some theorists have proposed retrocausal interpretations of quantum mechanics where future measurements can influence past quantum states, further complicating traditional temporal causality. Quantum mechanics also challenges traditional temporal ordering through phenomena like entanglement, where correlated quantum systems exhibit spooky action at a distance that seems to transcend normal causal sequences. These quantum puzzles suggest that our conventional understanding of how reality evolves through time may be fundamentally incomplete. Applied to cosmology, these considerations raise the possibility that the universe's apparent evolution through time, including its apparent beginning, might look very different when viewed through the lens of a more complete quantum theory of gravity, potentially revealing temporal concepts like beginning and always existed to be approximations that break down when applied to reality at its most fundamental level. Time's fundamental nature, whether it flows, exists as a dimension, emerges from deeper principles, or represents a psychological construct, has profound implications for how we conceptualize cosmic origins. If time is not fundamental but emergent, questions about the beginning of everything might need reformulation in terms of the more basic structures from which time emerges. If multiple temporal dimensions exist, as some speculative theories suggest, linear notions of beginning and ending might prove inadequate. If time is fundamentally discrete rather than continuous, as certain quantum gravity approaches propose, the concept of an absolute first moment might require reconceptualization. Perhaps most fundamentally, if time itself represents an approximate description valuable for certain scales and contexts, rather than a basic feature of reality, then absolute temporal concepts like always or beginning might not apply to reality at its deepest level. Physicist Carlo Rovelli captures this perspective. The absence of time does not mean that everything is frozen and immobile. It means that the elementary equations of the world are not written in terms of time. This view suggests that our temporal concepts, while enormously useful for daily life and much of science, might ultimately be inadequate for describing reality's deepest layer, similar to how Newtonian physics, while perfectly adequate for everyday experiences, breaks down under extreme conditions where relativistic or quantum effects become significant. As we contemplate whether the universe had a beginning or has always existed, we may need to recognize that these temporal framings themselves might represent approximations that obscure rather than illuminate the ultimate nature of cosmic origins. The most fundamental mystery we face when contemplating our universe isn't simply where all the matter and energy came from, but rather how the deep structures that govern reality, the laws of physics themselves, came to be. When we ponder the existence of anything at all, rather than nothing, we inevitably confront this meta-question: are the laws of physics themselves eternal, existing outside time and space, or did they somehow emerge alongside our universe? For centuries, philosophers and scientists alike have wondered whether mathematical truths are discovered or invented. Platonists argue that mathematical truths exist independently of human minds, that they are eternal and unchanging. According to this view, When physicists uncover the mathematical relationships that describe gravity or quantum mechanics, they're not inventing these relationships but discovering pre-existing truths. If this perspective holds merit, perhaps the universe exists because these mathematical structures necessitate it. The mathematical universe hypothesis, championed by physicist Max Tegmark, suggests something even more profound, that physical reality isn't just described by mathematics, it is mathematics. According to this hypothesis, the universe doesn't just follow mathematical laws, it's a mathematical structure itself. This radical idea proposes that our external physical reality is a mathematical structure, and that all mathematically possible structures exist as parallel universes. In essence, the universe exists because mathematical existence and physical existence are one and the same. When we contemplate our universe's remarkable properties, we find ourselves confronting the mysterious fine-tuning of fundamental constants, the gravitational constant, the strength of the electromagnetic force, the mass of elementary particles. All these parameters seem precisely calibrated to allow the formation of stars, planets, and ultimately, life. If any of these constants differed by even a minuscule amount, our universe would be dramatically different, possibly incapable of supporting complex structures. Some physicists interpret this fine-tuning as evidence for a deeper order, perhaps a more fundamental theory from which these constants naturally emerge. String theory, for instance, attempts to unify all forces and particles into a single theoretical framework, potentially explaining why these constants have the values they do. These strings exist in higher dimensional space, with our familiar four-dimensional space-time emerging as a kind of projection. Another intriguing concept in modern physics is symmetry breaking. In the extreme heat of the early universe, the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces may have been unified as a single force. As the universe expanded and cooled, this unified force split into the distinct forces we observe today, similar to how water vapor condenses into liquid water as temperature decreases. This process, known as spontaneous symmetry breaking, could explain how complexity emerged from simplicity. Symmetry breaking might offer a clue to how something could emerge from nothing, in a perfectly symmetrical state, a state of perfect balance and uniformity. There's no reason for anything to happen, for any change to occur. But if this symmetry is unstable, even the slightest perturbation could trigger a cascade of changes, giving rise to structure and complexity. Perhaps the laws of physics themselves emerged from such a symmetry-breaking event, transitioning from a state of perfect symmetry, which one might equate with nothing, to the complex, structured reality we observe. The anthropic principle offers another perspective on the origin of physical laws. This principle, in its weak form, states that the observed values of physical constants must be compatible with the existence of observers like us. In other words, we shouldn't be surprised to find ourselves in a universe governed by laws that allow our existence. If these laws were different, we wouldn't be here to observe them. The strong anthropic principle goes further, suggesting that the universe must have properties that allow life to develop at some point in its history. Under this principle, the laws of physics are, in a sense, explained by the necessity of observers. While this doesn't directly explain the origin of physical laws, it suggests that their particular form may be constrained by the requirement that conscious beings eventually evolve to contemplate them. But what if the laws of physics aren't universal? What if they vary across different regions of space or time, or across different universes within a multiverse? The string theory landscape suggests the possibility of 10 to the power of 500 different stable vacuum states, each corresponding to a universe with different physical laws. If this is true, our universe's particular set of physical laws might be just one manifestation among countless possibilities, selected not by necessity but by chance or by anthropic considerations. The distinction between fundamental and emergent laws is crucial. Some physicists argue that what we perceive as fundamental laws, like quantum mechanics or general relativity, might actually be emergent phenomena, arising from deeper, more fundamental principles, similar to how the laws of thermodynamics emerge from the statistical behavior of countless particles. Perhaps the true fundamental laws are simpler, more elegant, more necessary than those we currently recognize. The search for a theory of everything exemplifies this quest for the most fundamental laws. Physicists hope to find a single theoretical framework that encompasses all physical phenomena, from the behavior of subatomic particles to the large-scale structure of the universe. Such a theory would not only unify our understanding of nature, but might also shed light on why the universe is governed by laws at all, and why these particular laws. One candidate for such a theory is loop quantum gravity, which attempts to reconcile quantum mechanics with general relativity by describing space-time as a network of finite loops woven together in a complex structure. According to this theory, space and time themselves emerge from more fundamental quantum processes, suggesting that the laws governing these processes might be the most fundamental laws of all. But do any of these approaches truly explain the origin of physical laws? Even if we discover the most fundamental theory, we're still left with the question, why this theory and not another? What makes these particular mathematical structures correspond to physical reality? Some philosophers argue that the laws of physics don't govern reality at all, but rather describe patterns and regularities in physical phenomena. According to this view, the laws aren't external constraints imposed on the universe, but descriptions of how the universe behaves. This perspective shifts the question from where did the laws come from to why does the universe exhibit regular, describable patterns? The information-theoretic interpretation of physics offers one answer. According to this view, physical laws represent the most efficient way to process information about the universe. The laws we observe might be those that maximize the computational efficiency of the universe, allowing it to evolve in the most information-rich way possible. This brings us to another provocative idea. Could our universe be a simulation? If so, the laws of physics might be analogous to the code that governs the simulation, established by the simulators for their own purposes. While this doesn't ultimately explain the origin of physical laws, it merely pushes the question back to the laws governing the reality in which the simulation runs. It offers an intriguing perspective on the nature of physical law. Some theorists have proposed that the laws of physics might evolve through a process analogous to natural selection. In this view, universes with certain laws might be better at reproducing, perhaps through the creation of black holes that spawn new universes with similar laws. Over cosmic time, this cosmic natural selection would favor universes with laws that maximize more fundamental principles, but from self-consistency requirements. According to this approach, the various particles and forces in the universe must pull themselves up by their bootstraps, forming a self-consistent whole where each element is what it is because of its relationships with all other elements. This brings us back to the mathematical universe hypothesis. If the universe is a mathematical structure, perhaps the laws of physics are simply the properties of this structure. They don't come from anywhere. They're inherent in the structure itself, just as the properties of a circle are inherent in its definition. The question, why these laws, then becomes, why this mathematical structure, which might be answerable in terms of mathematical necessity or consistency. Perhaps the most profound insight from modern physics is that the distinction between something and nothing is far more complex and subtle than it appears. The quantum vacuum, often described as the closest physical analog to nothing, is actually a seething sea of virtual particles, energy fluctuations, and quantum fields. The absolute nothing of philosophical conception, the complete absence of anything at all, may not be physically possible or even logically coherent. If true nothing is impossible, perhaps the existence of something, whether it's our universe, a multiverse, or some more fundamental substrate, is necessary rather than contingent. Perhaps existence itself is inevitable, not due to some external cause or reason, but because non-existence is not a coherent possibility. This perspective suggests a radical inversion of the traditional question about the universe's origin. Instead of asking, why is there something rather than nothing, we might ask, why would we expect there to be nothing? If existence is the default state, the necessity of being rather than non-being, then the existence of physical laws, whatever their specific form, might also be necessary rather than contingent. As we reach toward the most fundamental questions about the origin of physical law, we find ourselves at the boundary between physics and philosophy, between empirical investigation and logical speculation. Perhaps the ultimate answers lie beyond this boundary, in realms that human thought cannot fully penetrate, or perhaps they lie in a revolution in our understanding, a paradigm shift that will transform how we think about existence, causality, and law. What remains clear is that the search for the origin of physical laws continues to drive scientific progress, pushing us toward deeper and more comprehensive theories of nature. Whether these theories will ultimately explain why there are laws at all, or whether this question will remain forever at the frontier of human understanding, is itself one of the great mysteries of our intellectual quest. As we transition from considering whether physical laws can explain the universe's origin to confronting the limits of human knowledge itself, we must acknowledge that even our most sophisticated theories may never fully answer the most fundamental questions. Perhaps the greatest insight from modern physics is not any specific theory or equation, but the recognition of how vast and profound the mysteries of existence truly are. As we venture deeper into our quest to understand the universe's origin, we inevitably confront a sobering possibility. What if the ultimate truth lies beyond our cognitive reach? What if the human mind, remarkable as it is, simply lacks the capacity to fully comprehend the deepest nature of reality? This isn't merely a question of technological limitations or insufficient data, though these certainly present substantial challenges, but a more fundamental concern about the limits of human knowledge itself. Our observational limitations are perhaps the most obvious constraint. We are, quite literally, trapped within our cosmic horizon, the spherical boundary beyond which light has not had time to reach us since the beginning of the universe. This horizon, approximately 46 billion light-years in radius, represents the absolute limit of what we can directly observe. Anything beyond this boundary is, by definition, unobservable to us, no matter how advanced our telescopes become. This means that roughly 95% of the universe lies forever beyond our observational reach, hidden behind this cosmic veil. Even within our observable universe, we face severe practical limitations. The further we look into space, the further back in time we see due to the finite speed of light. This means that we observe distant regions of the universe not as they are now, but as they were billions of years ago. This time delay creates a fundamental barrier to our understanding of the current state of the cosmos as a whole. We can never obtain a complete, simultaneous snapshot of the universe. Our view is always fragmented across different cosmic epochs. Moreover, our observations are limited by the types of signals we can detect. Electromagnetic radiation, from radio waves to gamma rays, provides our primary window into the cosmos. But what if crucial aspects of reality don't interact with electromagnetic fields? Dark matter, which appears to make up about 27% of the universe's mass energy content, is invisible to our telescopes precisely because it doesn't interact with light. We can infer its existence through its gravitational effects, but its fundamental nature remains elusive. What other aspects of reality might we be missing entirely because they don't register on our observational instruments? When it comes to understanding the absolute beginning of the universe, our observational limitations become even more severe. The earliest epoch we can directly observe is the cosmic microwave background radiation, which dates to approximately 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to form neutral hydrogen atoms, allowing light to travel freely for the first time. Everything before this surface of last scattering is hidden from direct electromagnetic observation, shrouded in what cosmologists call the cosmic dark age. Recent technological advances have begun to probe earlier epochs through gravitational waves, neutrinos, and other non-electromagnetic messengers. The detection of primordial gravitational waves could potentially provide a window into the inflationary epoch, just fractions of a second after the Big Bang. But even gravitational waves can't penetrate all the way back to the hypothetical t equals 0, the moment of creation itself, if such a moment existed. The Planck epoch, the infinitesimal fraction of the first second after the Big Bang, when the universe was younger than 10 to the negative 43 seconds and smaller than the Planck length, approximately 10 to the negative 35 meters, represents the absolute limit of our theoretical understanding. At this scale, both quantum mechanics and general relativity break down, and we have no verified physical theory to describe what happens. This isn't merely a gap in our knowledge that future theories might fill. It may represent a fundamental limit to what can be known through the methods of empirical science. Can we ever devise experiments that test the absolute beginning? The energy scales involved in the earliest moments of the universe are far beyond what particle accelerators like the Large Hadron Collider can achieve. To recreate the conditions of the Planck epoch would require a particle accelerator the size of the galaxy. Even then, we would only be creating local conditions similar to the early universe, not observing the beginning itself. Some cosmologists have proposed that certain features of the cosmic microwave background radiation might carry imprints of processes from the pre-inflationary universe, potentially providing indirect evidence about what came before. Others suggest that the distribution of galaxy clusters or the polarization patterns in the cosmic microwave background might reveal signatures of collisions between our universe and others in a multiverse scenario. But these approaches rely on theoretical models that are themselves unverified, creating a circular problem where the evidence for a theory depends on assuming the theory is correct. Perhaps we might look to mathematics for answers that observational cosmology cannot provide. Mathematical consistency might constrain the space of possible universe types, potentially revealing why our universe has the properties it does. But this approach faces its own limitations. As Kurt Gödel demonstrated with his incompleteness theorems, even mathematics itself has inherent limitations. There are true statements within any sufficiently complex mathematical system that cannot be proven within that system. If mathematics cannot achieve complete self-consistency, how can we expect it to provide a complete description of physical reality? The multiverse hypothesis presents another challenge to our quest for ultimate knowledge. If our universe is just one of many in a vast multiverse, each with potentially different physical laws, we may never be able to observe or interact with these other universes. They would exist beyond our cosmic horizon, separated from us by expanses of space-time that no signal can cross. The multiverse might be true, but if it's empirically unverifiable, does it qualify as scientific knowledge? Some philosophers of science, following Karl Popper, argue that a theory must be falsifiable to be scientifically meaningful. If a theory makes no testable predictions that could potentially prove it wrong, it crosses the boundary from science into metaphysics. By this criterion, certain multiverse theories, particularly those that posit universes with which we can have no causal contact, may be inherently untestable, and therefore outside the realm of scientific knowledge. Then there's the question of whether human cognition itself imposes fundamental limits on our understanding. Our brains evolved to navigate the mesoscale world of everyday objects moving at moderate speeds, not the quantum realm of subatomic particles or the cosmological scale of galaxy superclusters. Our intuitions about causality, determinism, locality, and continuity emerged from evolutionary pressures that had nothing to do with understanding the fundamental nature of reality. Quantum mechanics offers a stark illustration of this cognitive limitation. After more than a century of study, physicists have developed mathematical formalisms that accurately predict quantum phenomena with extraordinary precision. Yet there's no consensus on what quantum mechanics tells us about the nature of reality. The various interpretations, Copenhagen, many worlds, pilot wave, cubism, and others, make identical empirical predictions, but suggest radically different pictures of what's really happening. This interpretive flexibility suggests that quantum reality may be fundamentally alien to human intuition, perhaps even beyond our capacity to visualize or conceptualize. Similar cognitive limitations may apply to our understanding of time. Our conscious experience imposes a strict arrow of time, with the past fixed and the future open. Yet physics suggests a more complex picture. In Einstein's relativity, the distinction between past, present, and future is relative to the observer's reference frame. In quantum mechanics, some phenomena seem to involve retrocausality, effects preceding their causes. These counterintuitive aspects of temporal physics suggest that our innate sense of time may be inadequate for comprehending the true nature of cosmic temporality. The problem of consciousness itself presents another frontier of human knowledge. How does subjective experience arise from physical processes in the brain? Despite decades of research in neuroscience, psychology, and philosophy of mind, consciousness remains what philosopher David Chalmers calls the hard problem, a puzzle that seems resistant to conventional scientific approaches. If we cannot fully understand the conscious mind that does the knowing, can we ever fully trust what we think we know about external reality? Some philosophers go further, suggesting that certain questions may be mysterious, inherently unanswerable given the structure of human cognition. Just as a dog cannot understand calculus, no matter how well it's explained, perhaps humans cannot understand certain aspects of ultimate reality, no matter how much evidence we gather or how sophisticated our theories become. This position, known as cognitive closure, suggests that just as there are concepts inaccessible to simpler minds, there may be truths about the universe that lie permanently beyond human comprehension. But technological advances offer some hope of transcending these limitations. Artificial intelligence systems already outperform humans in specific domains, from playing chess and Go to predicting protein structures and discovering new mathematical theorems. As AI systems become more sophisticated, they may help us explore theoretical spaces beyond human intuition, potentially uncovering patterns and relationships invisible to unaided human cognition. Quantum computing represents another technological frontier that could extend our cognitive reach. Classical computers struggle with simulating quantum systems due to the exponential growth in computational resources required as the system size increases. Quantum computers, which exploit quantum superposition and entanglement, might eventually allow us to simulate complex quantum systems that are currently beyond our computational capabilities, potentially providing insights into quantum gravity and early universe cosmology. Brain-computer interfaces and cognitive enhancement technologies might eventually augment human cognitive capabilities, allowing us to develop intuitions for realms currently beyond our mental grasp. Just as mathematical notation and scientific instruments have expanded the reach of human thought, future neural technologies might further extend our cognitive horizons, allowing us to conceptualize aspects of reality currently hidden from our understanding. But even with technological assistance, certain knowledge limits may remain insurmountable. The anthropic principle reminds us that our observations are inherently biased by the fact that we exist to make them. We inevitably observe a universe compatible with our existence, which may give us a skewed perspective on the range of possible physical realities. If most of the multiverse is hostile to life, we will never observe those regions, creating a selection bias in our cosmic worldview. The horizon problem in cosmology illustrates another fundamental limit to knowledge. Regions of the universe separated by sufficient distance have never had time to exchange information. They lie outside each other's light cones. This means that no natural process can have established causal connections between them. Yet the cosmic microwave background radiation shows remarkable uniformity across these causally disconnected regions, suggesting they somehow know about each other. Cosmic inflation provides one potential explanation for this correlation, but the inflationary epoch itself lies beyond direct observation, leaving us to infer its existence from its consequences rather than observing it directly. Perhaps the most profound limitation on our understanding comes from the problem of initial conditions. Even if we had a complete theory of everything that unified all physical forces and explained all fundamental particles, such a theory wouldn't necessarily tell us why the universe began in the particular state it did. The initial conditions of the universe, the specific configuration of fields and particles at the beginning, appear to be contingent rather than necessary. No physical theory can explain why these conditions, rather than others obtained at the beginning, because physical theories explain how states evolve from previous states. They don't explain the first state itself. Some physicists propose that the initial conditions might be explained by a no-boundary proposal, or similar approaches that eliminate the need for boundary conditions by making time itself emerge from a more fundamental timeless state. But these proposals remain speculative and face their own conceptual challenges. The quest to explain why the universe began in its particular state may ultimately prove as elusive as the quest to explain why there is something rather than nothing. The role of consciousness in quantum mechanics presents another frontier of fundamental uncertainty. According to some interpretations, measurement and observation play a crucial role in collapsing quantum superpositions into definite states. This suggests that consciousness might be more deeply intertwined with physical reality than classical physics would indicate. If true, this raises profound questions about the relationship between mind and matter that may resist resolution through conventional scientific approaches. The limits of reductionism present another potential barrier to complete knowledge. The traditional scientific approach seeks to understand complex systems by breaking them down into simpler components and studying their interactions. But emergent phenomena, from consciousness to ecosystems to social systems, often display properties that cannot be predicted from understanding their components in isolation. If the universe as a whole exhibits emergent properties that cannot be reduced to the behavior of its parts, a purely reductionist approach may never yield complete understanding. Despite these limitations, the history of science offers grounds for cautious optimism. Time and again, problems that seemed intractable have yielded to persistent inquiry and conceptual innovation. The atom was once thought to be indivisible. Now we understand subatomic particles in exquisite detail. The mechanisms of heredity were once mysterious. Now we can read and write the genetic code. The boundaries of the knowable have expanded dramatically over centuries of scientific progress. Moreover, we can often achieve functional understanding without complete knowledge. Engineers built practical steam engines before thermodynamics was fully formalized. Physicians prescribed aspirin effectively long before its mechanism of action was understood. Even if absolute knowledge of cosmic origins remains elusive, we may still develop increasingly accurate and useful models that capture essential features of reality, even if they don't represent the ultimate truth. The role of artificial intelligence in future discoveries may be transformative. AI systems are already helping scientists analyze vast datasets, identify patterns too subtle for human recognition, and explore theoretical spaces too complex for unaided human intuition. As these systems become more sophisticated, they may help us identify crucial connections and relationships that have eluded human researchers, potentially leading to breakthroughs in our understanding of fundamental physics and cosmology. Neural networks, in particular, have demonstrated remarkable abilities to identify patterns in complex data without being explicitly programmed to look for specific features. Applied to cosmological data, such systems might identify subtle signatures of pre-Big Bang physics or evidence for particular multiverse models that human analysts would overlook. The combination of human creativity and machine pattern recognition might prove more powerful than either approach alone. Quantum computing represents another technological frontier that could expand our knowledge horizons. Classical computers struggle to simulate quantum systems because the computational resources required grow exponentially with the system size. Quantum computers, which harness quantum superposition and entanglement, might eventually overcome this limitation, allowing us to simulate complex quantum systems currently beyond our computational reach. This could provide crucial insights into quantum gravity, the earliest moments of the universe, and other phenomena at the frontier of physics. Space exploration will continue to expand our observational capabilities. Telescopes positioned far from Earth, in solar orbit or even beyond the solar system, could provide new perspectives on the cosmos, free from Earth's atmospheric interference, and potentially offering baselines for parallax measurements on an interstellar scale. Future gravitational wave observatories might detect primordial gravitational waves from the inflationary epoch, providing a window into the earliest moments of cosmic history. Multi-messenger astronomy, combining observations across the electromagnetic spectrum with gravitational waves, neutrinos, and other carriers of information, will provide increasingly comprehensive views of cosmic phenomena. New physics facilities on Earth, such as next-generation particle accelerators and ultra-sensitive dark matter detectors, will probe fundamental physics at unprecedented energy scales and sensitivities. While these may not directly observe the beginning of the universe, they could provide crucial pieces of the puzzle, constraining theoretical models and potentially revealing new particles or forces that shape cosmic evolution. But even with these technological advances, certain knowledge horizons may remain beyond our reach. The multiverse, if it exists, may be empirically unverifiable. The state of the universe before the Big Bang, if such a concept is even coherent, may leave no detectable traces in our observable cosmos. The ultimate nature of consciousness, the reason for existence itself, and other profound mysteries may resist final resolution through scientific inquiry. In facing these limits, we might find wisdom in the ancient Socratic insight that true knowledge begins with acknowledging what we don't know. Perhaps the most profound scientific and philosophical stance is not claiming to have all the answers, but remaining open to the vastness of what remains unknown and possibly unknowable. This intellectual humility doesn't diminish the value of scientific inquiry. Rather, it places science in its proper context as a powerful but limited tool for understanding reality. The quest to understand the universe's origins will continue to drive scientific progress, inspiring new theories, experiments, and observations. Even if we never arrive at complete knowledge of cosmic beginnings, the journey itself yields valuable insights, technologies, and perspectives. The scientific exploration of cosmic origins represents one of humanity's noblest intellectual endeavors, a collective attempt to comprehend our place in the vast cosmic drama. As we transition from considering the limits of human knowledge to exploring the future of cosmology, we should remember that today's cutting-edge research will someday be viewed as merely the beginning of a much longer scientific journey. Just as Newton's physics, revolutionary in its time, was later subsumed into Einstein's more comprehensive framework, our current theories may eventually be incorporated into deeper understandings that we cannot yet imagine. The recognition of our knowledge limits need not lead to despair or nihilism. Rather, it can inspire a sense of wonder at the vastness and complexity of the cosmos, and humility in the face of mysteries that continue to elude our understanding. There is profound beauty in the realization that we are finite beings attempting to comprehend the infinite, that our quest for knowledge, while eternally incomplete, connects us to something far greater than ourselves. Perhaps the greatest wisdom lies in balancing confidence in what we know with openness to what remains unknown, in developing increasingly sophisticated theories while recognizing their inevitable limitations. In this balance, we find the true spirit of scientific inquiry, not dogmatic certainty, but persistent curiosity, not the claim to final truth, but the endless quest to deepen our understanding of the magnificent cosmic reality we inhabit. As we look toward the future of cosmology and the ongoing search for the universe's origins, we can be certain of one thing: the journey will continue, with each discovery opening new questions, each answer revealing new mysteries, in an endless adventure of cosmic exploration that may well be one of humanity's greatest and most enduring legacies. The quest to understand the universe's origins represents one of humanity's most ambitious intellectual endeavors. While we've made remarkable progress, particularly in the last century, the most fundamental questions remain open, yet the future of cosmology holds extraordinary promise, with emerging technologies, theoretical breakthroughs, and observational capabilities that might finally illuminate the deepest cosmic mysteries. The next generation of astronomical observatories represents our most immediate hope for new cosmic insights. On the ground, massive telescopes like the Extremely Large Telescope, ELT, in Chile, with its 39-meter primary mirror, will gather unprecedented amounts of light from the distant universe. This extraordinary light-collecting power will allow astronomers to observe the first galaxies that formed after the Big Bang, providing crucial data about the universe's early evolution. In space, the recently launched James Webb Space Telescope marks just the beginning of a new era of cosmic observation. Webb's infrared capabilities allow it to peer through cosmic dust and observe objects from the universe's infancy, including stars and galaxies that formed just a few 100 million years after the Big Bang. Future space observatories will build on Webb's capabilities, with even more sensitive instruments designed to study specific aspects of cosmic evolution. Perhaps most exciting are the planned gravitational wave observatories, which promise to open an entirely new window into cosmic history. Current facilities like LIGO and Virgo can detect ripples in space-time caused by violent cosmic events like black hole mergers. But future observatories, particularly space-based facilities like LISA, Laser Interferometer Space Antenna, will be sensitive to gravitational waves at different frequencies, potentially including primordial gravitational waves generated during the inflationary epoch, mere fractions of a second after the Big Bang. The detection of primordial gravitational waves would represent a monumental breakthrough, providing direct observational evidence of the inflationary period that many cosmologists believe immediately followed the Big Bang. These ancient ripples in space-time would carry information about the universe at energy scales far beyond what particle accelerators could ever achieve, offering our first direct glimpse of physics near the Planck scale. Neutrino astronomy represents another promising frontier. These ghostly particles interact only weakly with matter, allowing them to travel unimpeded across vast cosmic distances. Unlike light, which can only reach us from after the universe became transparent, about 380,000 years after the Big Bang, neutrinos could potentially carry information from much earlier epochs. The continued development of large-scale neutrino detectors, like IceCube in Antarctica and its planned successors, might eventually allow us to detect the cosmic neutrino background, the neutrino equivalent of the cosmic microwave background radiation. Multi-messenger astronomy, the coordinated observation of cosmic events using different types of signals, including electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays, represents a particularly promising approach. By combining these different information carriers, astronomers can build more complete pictures of cosmic phenomena than would be possible from any single type of observation. Advances in particle physics will also contribute vital pieces to the cosmic puzzle. The Large Hadron Collider has already discovered the Higgs boson, confirming a crucial component of the standard model of particle physics. Future accelerators, like the proposed Future Circular Collider with a 100-kilometer circumference, would achieve even higher energies, potentially discovering new particles and interactions that played crucial roles in the early universe. Of particular interest are particles that might constitute dark matter, which makes up about 27% of the universe's mass-energy content, but whose fundamental nature remains unknown. Similarly, understanding dark energy, the mysterious force driving the accelerating expansion of the universe, remains a central goal of future cosmology. Constituting about 68% of the universe's mass-energy content, dark energy's fundamental nature remains one of the greatest puzzles in physics. Future surveys of galaxy distributions will map the large-scale structure of the universe with unprecedented precision, tracking the influence of dark energy on cosmic expansion throughout history. Theoretical advances will proceed in parallel with these observational efforts. Quantum gravity, the long-sought unification of quantum mechanics and general relativity, remains the holy grail of theoretical physics. Current approaches like string theory, loop quantum gravity, and causal set theory each offer promising insights, but none has emerged as definitively correct. Future theoretical work, guided by new observations and perhaps aided by advanced computational tools, might finally resolve this fundamental challenge. Artificial intelligence and machine learning will increasingly transform how we analyze cosmic data and develop theoretical models. AI systems have already demonstrated remarkable abilities to identify patterns in complex datasets, from detecting gravitational wave signals in noisy detector data to classifying galaxies in astronomical images. Future AI systems might identify subtle patterns in cosmic observations that human analysts would miss, potentially revealing signatures of exotic physics or pre-Big Bang phenomena. Beyond pattern recognition, AI might help generate and evaluate theoretical models. The space of possible physical theories is vast, and human theorists can explore only a tiny fraction of it. AI systems could potentially search this space more efficiently, identifying promising theoretical frameworks that satisfy known constraints while making novel predictions. Quantum computing represents another technological frontier with profound implications for cosmology. Classical computers struggle to simulate quantum systems because the computational resources required grow exponentially with system size. Quantum computers, which harness quantum superposition and entanglement, could potentially overcome this limitation, allowing us to simulate complex quantum systems that are currently computationally intractable. These simulations could provide insights into quantum aspects of the early universe, potentially including quantum gravity effects. Space exploration will also contribute to our understanding of cosmic origins, albeit indirectly. As we venture beyond Earth, establishing observatories on the Moon or in distant solar orbits, we gain new perspectives on the cosmos, free from Earth's atmospheric interference. These remote observatories could form interferometers with unprecedented baselines, achieving angular resolutions far beyond current capabilities. While these technological and observational advances offer tremendous promise, will we ever truly observe the absolute beginning of the universe? The answer remains uncertain. The earliest epoch we can currently observe directly is the cosmic microwave background. Dating to about 380,000 years after the Big Bang, gravitational waves and neutrinos might eventually push this observational horizon back to the first second or even earlier. but reaching all the way back to the hypothetical t equals 0, the moment of creation itself, presents formidable challenges. The Planck epoch, the period before the universe was 10 to the negative 43 seconds old, represents a particularly difficult barrier. At this scale, our current physical theories break down, and we have no verified framework for describing what happens. While future theories of quantum gravity might provide mathematical models of this epoch, directly testing these models through observation may prove impossible due to fundamental physical limits rather than merely technological ones. This raises a profound question. If we cannot directly observe the beginning, can we ever know with certainty how the universe began? Perhaps we can approach this question indirectly, through a combination of theoretical consistency, observational constraints on later epochs, and philosophical considerations. If a particular theory of cosmic origins makes precise predictions about observable phenomena, and those predictions are consistently confirmed by observation, we might gain increasing confidence in the theory's account of the unobservable beginning. Will humanity ever reach a point of complete understanding? The history of science suggests caution. Each major breakthrough has typically revealed new questions and mysteries rather than providing final answers. Newton's gravitational theory seemed comprehensive until Einstein's relativity revealed its limitations. Einstein's relativity and quantum mechanics transformed our understanding of space, time, and matter, but their incompatibility at the Planck scale points to deeper truths we have yet to discover. This pattern suggests that our quest for understanding might be asymptotic, continuously approaching but never quite reaching complete knowledge. Each generation's theories provide more accurate and comprehensive models than those of the previous generation, but each model remains an approximation, a useful representation rather than the final truth. Perhaps the universe's absolute beginning, if such a concept even makes sense, lies at the asymptotic limit of this progression, eternally approached but never fully grasped. Yet this perspective need not diminish the value of the quest. The journey toward understanding has immense practical and philosophical value, regardless of whether we ever reach the ultimate destination. Each step reveals new aspects of cosmic reality, deepens our appreciation of nature's complexity and beauty, and potentially enables new technologies and applications. What might be the next big discoveries that could transform our understanding of cosmic origins? Several possibilities stand out. The detection of primordial gravitational waves would provide crucial evidence about the inflationary epoch and potentially reveal signatures of quantum gravity. The direct detection of dark matter particles would illuminate a crucial component of the cosmic composition whose nature has remained elusive for decades. A comprehensive theory of quantum gravity, supported by observational evidence, would provide a unified framework for understanding the earliest moments of cosmic history. Beyond these anticipated breakthroughs, we should remain open to unexpected discoveries that might fundamentally reshape our cosmic understanding. The history of science is filled with serendipitous observations and theoretical insights that transformed entire fields. Similar surprises surely await future cosmologists. The role of space exploration in driving cosmic discovery shouldn't be underestimated. As humanity establishes a permanent presence on the Moon and eventually Mars, we gain new platforms for astronomical observation, free from Earth's atmospheric interference and light pollution. Lunar observatories on the far side of the Moon would be shielded from Earth's radio noise, enabling sensitive radio astronomy that could detect signals from the cosmic dark age. Will humanity ever achieve a complete understanding of cosmic origins? The honest answer is that we don't know. The universe might be structured in ways that make certain aspects of its nature permanently inaccessible to human understanding, whether due to fundamental physical limits on observation or cognitive limits on human comprehension. Alternatively, through persistent inquiry, technological innovation, and theoretical creativity, we might eventually develop a comprehensive understanding that answers even the most fundamental questions about cosmic beginnings. What seems certain is that the quest itself will continue, driven by the same curiosity and wonder that has propelled cosmic exploration throughout human history. Each generation builds on the discoveries of the previous one, pushing the boundaries of knowledge further and developing more sophisticated tools for cosmic exploration. This multi-generational project represents one of humanity's noblest endeavors, a collective attempt to understand our place in the vast cosmic drama. The search for the universe's origins also carries profound philosophical implications that extend beyond physics and astronomy. As we gain deeper insights into cosmic history, we inevitably confront questions about meaning, purpose, and our place in the grand cosmic scheme. These questions lie at the interface of science, philosophy, and in some contexts, theology. Education and public engagement play crucial roles in this process. By communicating the excitement and significance of cosmological research to the broader public, scientists inspire future researchers and build societal support for ambitious scientific endeavors. The stunning images from space telescopes, the elegant mathematics of theoretical models, and the fascinating narratives of cosmic evolution all contribute to a shared cultural understanding of our place in the universe. International collaboration has become increasingly important in cosmological research, with major facilities like the Large Hadron Collider and the Square Kilometre Array representing global rather than national efforts. This collaboration transcends political and cultural boundaries, uniting humanity in a shared quest for understanding. Future breakthroughs in cosmic understanding will likely emerge from such collaborative efforts, combining diverse perspectives, expertise, and resources. As we look ahead to the future of cosmology, we should maintain a balance between ambition and humility. Ambition drives us to tackle the most profound questions, to build increasingly sophisticated instruments, and to propose bold theoretical frameworks. Humility reminds us of the vastness and complexity of the cosmos, the limitations of human understanding, and the provisional nature of scientific knowledge. This balance, this cosmic perspective, represents one of the greatest gifts that cosmology offers to human culture. The future of cosmology holds extraordinary promise. Through persistent inquiry, technological innovation, and theoretical creativity, future researchers will continue to deepen our understanding of cosmic origins and evolution. While certain aspects of the absolute beginning might remain shrouded in mystery, our knowledge will continue to expand, revealing ever more of the magnificent cosmic tapestry of which we are a part. As our cosmic journeys comes full circle, we return to the fundamental question that launched our exploration. Was there ever truly nothing? After traversing the intellectual landscape of modern cosmology, from the Big Bang to quantum fluctuations, from multiverse theories to the limits of human knowledge, what answer can we offer to this profound query? The honest response remains: we don't know with certainty, but our uncertainty is far richer and more nuanced than when we began. We have not found a definitive answer, but we have discovered how to ask better questions and recognize the profound complexity underlying what once seemed a simple dichotomy between something and nothing. What we do know is that the concept of absolute nothingness, the complete absence of space, time, matter, energy, and even physical laws, grows increasingly problematic the more deeply we examine it. The quantum vacuum, often described as the closest physical analog to nothing, is actually teeming with activity. Virtual particles popping in and out of existence, quantum fields extending through space, energy fluctuations governed by the principles of quantum uncertainty. If this is our universe's version of nothing, it is remarkably substantial. Modern physics has transformed our understanding of nothingness from a simple absence of things to a complex state governed by physical laws. But this transformation immediately raises a deeper question. Where did these laws come from? If quantum fields and physical principles existed before the universe, then there was never truly nothing. Some form of order, structure, or potential already existed. The concept of time itself complicates our question further. General relativity suggests that time is not absolute, but rather a dimension interwoven with space, forming the unified fabric of space-time. If the Big Bang represents the beginning of space-time itself, not just an event within pre-existing time, then asking what came before may be as meaningless as asking what lies north of the North Pole. There is no before if time itself begins with the universe. Quantum physics offers another perspective that challenges our intuitive notions of nothingness. Quantum indeterminacy suggests that at the most fundamental level, nature is probabilistic rather than deterministic. Particles exist in superpositions of states until measured, and their properties emerge from this measurement process rather than being predetermined. This intrinsic indeterminacy suggests that perhaps emptiness and existence are not absolute opposites, but exist on a continuum of probability and potentiality. Perhaps the quantum vacuum represents a state of pure potentiality, not absolutely nothing, but not yet manifested as something specific. In this view, our universe might have emerged not from absolute nothingness, but from a realm of pure potential, through a process that transformed possibility into actuality. The quantum vacuum would be not an empty stage, but a field of all possibilities, from which our particular reality condensed. Information theory provides yet another perspective. Some theoretical approaches suggest that information, not matter or energy, represents the most fundamental aspect of physical reality. In this view, the universe is essentially a system processing information, with physical phenomena emerging from patterns of information rather than existing as primary substances. If information is fundamental, then perhaps the origin of the universe represents not the emergence of something from nothing, but the organization of information into the specific patterns we recognize as physical reality. The multiverse hypothesis offers yet another reframing of our question. If our universe is just one of many in a vast multiverse, then the apparent beginning of our cosmos might not represent an absolute beginning, but merely a local event, the emergence of our particular bubble universe within a much larger, perhaps eternal, multiverse structure. In this scenario, there was never an absolute nothing, merely transformations and emergences within an eternally existing multiverse. Even if we accept that our universe had a beginning in the Big Bang, the evidence for cosmic inflation, a period of exponential expansion in the universe's first fraction of a second, suggests that this beginning was extraordinarily ordered and specific. The initial conditions of the universe appear to have been highly special, with an entropy far lower than might be expected from random chance. This specialness suggests that either our universe was somehow selected from among many possibilities, or that physical principles we don't yet understand naturally produce such ordered beginnings. The philosophical implications of these scientific perspectives are profound. Throughout history, the question of why there is something rather than nothing has often been framed as a choice between two alternatives. Either the universe emerged from absolute nothingness through some spontaneous process, or it was created by some transcendent cause or creator. Modern cosmology suggests a more nuanced landscape of possibilities. Perhaps the dichotomy between absolute something and absolute nothing is itself misleading, with reality emerging from states that defy such simple categorization. As we reflect on these scientific perspectives, we should remember that our understanding remains limited and provisional. Today's cutting-edge theories may eventually be superseded by deeper insights, just as Newtonian physics gave way to Einstein's relativity and quantum mechanics. The quest to understand the universe's beginning represents not a completed project, but an ongoing journey, with each generation building on and sometimes revolutionizing the insights of the previous one. This recognition of our limited knowledge shouldn't be seen as a failure, but as an honest acknowledgement of the magnitude of the question we're addressing. The fact that we can even contemplate the origins of the universe, formulate mathematical models of cosmic evolution, and devise experiments to test these models represents an extraordinary achievement of human intellect and creativity. That we haven't yet reached definitive answers speaks not to any inadequacy in our methods, but to the profound depth of the question itself. The scientific narrative of cosmic evolution offers its own kind of grandeur and meaning. From the initial singularity to the formation of galaxies, from the nuclear forging of elements in stellar furnaces to the emergence of planets and eventually life, the cosmic story reveals a universe of astonishing creativity and complexity. That we, products of this cosmic evolution, have developed the capacity to trace our origins back to the earliest moments of cosmic history represents a remarkable closing of the circle. The universe has evolved the capacity to understand itself. This scientific origin story doesn't answer all human questions about meaning and purpose, but it does provide a shared, evidence-based narrative that can unite humanity across cultural and religious boundaries. Whatever one's philosophical or theological perspective, the scientific account of cosmic evolution offers a common foundation for understanding our shared cosmic heritage and the remarkable journey that led from the Big Bang to human consciousness. As we consider the possibility that there was never absolute nothingness, that some form of potential or structure or mathematical reality may have always existed, we might feel both humbled and exalted. Humbled by the recognition that existence itself may be more fundamental than we can comprehend, with our universe representing not an absolute beginning, but a transformation within a deeper reality we're only beginning to glimpse. Exalted by the realization that we, composed of atoms forged in stellar explosions, have developed the capacity to contemplate these profound cosmic mysteries. Perhaps the most appropriate response to our original question, "Was there ever truly nothing?" is neither a confident affirmation nor a definitive denial, but a sophisticated agnosticism. We recognize the extraordinary progress we've made in understanding cosmic origins, while acknowledging the vast territories of knowledge that remain unexplored. We hold our current theories provisionally, valuing them for their explanatory power, while remaining open to new discoveries that might transform our understanding. If there's a concluding insight from our exploration, perhaps it's this: the boundary between being and non-being, between something and nothing, appears far more nuanced and permeable than our everyday experience suggests. At the foundations of reality, these seemingly absolute categories dissolve into probability distributions, quantum superpositions, and fields of potential. The emergence of our universe may represent not a discontinuous leap from absolute nothing to something, but a transformation within a deeper reality whose fundamental nature we're only beginning to glimpse. This insight doesn't diminish the mystery of existence, but enriches it. The question, "Why is there something rather than nothing?" remains as profound as ever, but our understanding of its terms has become more sophisticated. Both something and nothing have revealed unexpected depths and complexities, suggesting that reality itself transcends this simple dichotomy. As we continue our cosmic exploration, pushing the boundaries of observation and theory, we can expect further surprises and revelations. Whatever the future holds, the quest itself represents one of humanity's noblest endeavors, a collective attempt to comprehend the ultimate origins of the reality we inhabit. This quest connects us across cultures and generations, from ancient mythmakers to modern cosmologists, all grappling with the same profound question: where did all this come from? The universe began, or perhaps it always was, but the mystery of its origin is what keeps us searching for answers, driven by that uniquely human capacity for wonder, and that quintessentially scientific commitment to following the evidence wherever it leads. In this ongoing exploration, with each discovery revealing new mysteries and each answer generating new questions, we participate in the universe's own evolution toward greater consciousness and self-understanding. And in that participation lies perhaps the deepest meaning we can discover in our cosmic journey.